YouTube to see if the microphone is working, please. I'm going to get this back. I found the power. I'll make this one. Yes. It's now. We have this. Oh, here we go again. Hello, hello, hello. Hello, hello. Can you hear me? Hello, Mohammad. Ah, yeah, there is some delay on YouTube. Triple check. Is it working? Okay, perfect. How are you doing? I'm goodness to see you too.
Good. Or not?
I hope you enjoyed the workshop.
Yeah, I couldn't go in Eurosys because I was speaking at the same
Ah,
time.
yes, yes, yes,
I
yes.
come for some time because there are so many
So many things happening, right?
jumping.
Exactly. But nice to see you. So hello everyone. It's very nice to have you here. Very nice to have a full house for this third edition of the Memory-Centric Computing System workshop. Before anything, most of the material that you're going to see here today is available in your website. You can just scan this QR code and download the material over there. There's still some couple of slides that is going to be uploaded later on today, but this is your main reference to whatever is going to be presented here today if you want to follow up. Also, this is being live streamed and is on YouTube, so at some point, this might be a very dense type of workshop. We are going to try to cover a lot in the time that we have. And if you want to revisit any of the material, you can always check on YouTube. So before anything, just a brief self-introduction. Hello, I'm Geraldo. I'm a PhD graduate at the Safari Research Group. I've been working on processing memory architecture since my master's in 2016, and I did a PhD on that together with Professor Onur Mutlu in the Safari Research Group on the topics that you're going to cover here today. And we do research on not only on processing memory, but also computer architecture and systems as a whole. Just your last chance to get the QR code for the materials. I'm going to give 1, 2, 3, 4, 5. Perfect. Great.
By searching for MCCSys, ISCA,
And Google, yeah, it's going to come up. I would like to thank the organizers for this story. I'm not organizing this by myself. We have some of the organizers here present today that are going to discuss some of the topics, but some of the other are couldn't attend, unfortunately, due to other conference. But thank you so much for your contribution. So as I mentioned, the agenda is quite dense for today. We're going to do our best to cover as much as possible. We're going to have two initial talks from Professor Onur Mutlu and then Dr. Alper on the subject of processing memory. Then a very short coffee break. I don't know if there is coffee and where is the coffee is. If someone finds out, please let me know. I'll be very interested on that as well. But then you're going to move on with some other subjects on processing memory. I'm going to talk about some work that I did doing my PhD, and then you're going to have some more invited talks. So without further ado, Onur is going to give the first talk. Let me just do a quick context switch.
Welcome, everyone. It's great to have an almost full room. If people can find it, of course. Okay, can you change that?
Yes.
To the, yeah, you know. I think this workshop had the most registrations among all of them I have seen, but finding the room may be the most difficult part. So it's not just registrations. Location also matters, as you can see. And locality will matter also. Yeah. Okay. So this is actually our third incarnation of the MCCSys, which is a tutorial and workshop. But we have previously had a tutorial on memory-centric computing. We decided it became more of a workshop in the last three incarnations. So I think this is our maybe 9th time. I don't know. I haven't looked at it. In 2023, 2024, 2025. So you can call it the 9th time, let's say. Something is broken? Okay, go ahead.
Sorry.
Yeah. So I'm going to give an overview of what we will talk about to motivate things, and maybe talk about some things that are not going to be talked about later on. But feel free to ask questions. I don't need to cover all my slides. I have a lot of slides, as some of you may know, and we can go through them at very high bandwidth or low bandwidth. I prefer high bandwidth. Practice what I preach. But feel free to ask questions. Is it all good?
It's working now. Some problem with Zoom.
Zoom is not working. Yeah, maybe. Or I can join Zoom with my own laptop.
It could be fine. It's just the.
I thought this would be easier.
Me too. It's because of it's trying to share this one. Context switch is never.
Yeah. If someone figures out where coffee is, please let me know. I think I need coffee.
Is it now?
It's all good? Okay.
Oh, no, I'm going to keep it like this.
Okay, keep it like this. I think I don't need to look at the slides. Okay. Okay, so let's jump in. Today, computing is bottlenecked by data, and this is becoming much worse. Many applications are data intensive, and they're going to become even more data intensive in the future. The reason we have machine learning so exploding today is because of the availability of data and our ability to process it using new hardware architectures. And we want to do more, basically, more and more sophisticated analysis on data. I will go through some of these slides really quickly because I want to give time to our invited speaker and other speakers. But clearly, in machine learning, data is exploding. Compute requirements is also exploding. And that's why people are trying to explore different type of architectures, like wafer scale architectures, for example. I think those are very, very interesting efforts. But where they lack is really in the memory part. Because if you want to support huge amounts of data, you really need to have large memories that are at low cost. And when you go wafer scale and use something like SRAM, you're not low cost, basically. Okay, but it's good to explore those things. No question about that. But we're going to talk about large memories doing computation as opposed to putting memories very, very close to, or putting small memories to highly capable compute engines. They have their space also, so hopefully we'll see. Okay, there are other areas where data is exploding. Genomics, we do a lot of work in bioinformatics. And you have these devices, data generators, that can actually generate a lot of data, and people are generating a lot of data in genomics. I'm not going to talk about that. This is another area where we're seeing a huge data explosion, and data sizes actually don't fit. Forget about wafer scale. Data size don't fit DRAM. Data size don't fit storage even today. Like if you're doing genomic analysis on hundreds of terabytes of data, really you should go into storage or maybe larger scale systems. Okay, so basically the problem is today we have a huge data access problem. It's the major performance and energy bottleneck. I would also argue that it's robustness bottleneck. It's also security bottleneck. We had a DRAM-sec workshop earlier this morning. If you're interested, you can also find online. But the problem is our current design principles, the way we design essentially all of our computing systems cause great energy waste. We basically exacerbate this bottleneck. We keep moving data between the processor and memory, or wherever the data is generated and stored to a compute unit. And we keep doing that. This causes a lot of energy waste. I'm going to quantify some of these. This causes a lot of performance loss as well. And we identify this. We actually know that this causes a lot of performance loss, so we develop a lot of techniques that are very sophisticated, many levels of caching, many levels of prefetching, many levels of out-of-order execution at both software and hardware levels, and multi-threading to overcome this. Unfortunately, these techniques, sometimes they work. Many times they don't work quite well. And as a result, they compound the energy waste. So we're in this vicious cycle today where we're wasting a lot of energy in our computation, and then we're complaining about it. But maybe we should really solve the problem at its fundamental place, which is really not doing data movement. And that's what this workshop is all about. Memory-centric computing, minimizing data movement. Right. So today, we're not like that. Today, we're very processor-centric. All data needs to go to a processor. In fact, a very small fraction of that processor chip that I will show you at great system cost. This is a picture that I drew in 2008. It looks kind of similar today, but hopefully we'll see that there are also things changing to becoming more memory-centric today. Basically, if you look at this picture, the red parts are the cores. They could be heterogeneous. They could be accelerators. They could be any computation unit, basically. But they're not the majority of the chip. Most of the chip is really dedicated to storing and moving data. Caches, interconnects, memory, storage. And if you do the calculation, more than 95% of a single node is really dedicated to storage and data movement units. This is hardware cost, hardware area. And in a longer version of this talk, I would walk through 10 different processors, showing you this picture in real processors. You can do that. You can find that online. It is basically that. So, okay, basically, we are dedicating most of our hardware resources, which is important for sustainability. If you look at all the carbon footprint and sustainability, it's all about hardware cost, right, and hardware area that you use. But unfortunately, we're still bottlenecked by memory. I like taking the hat of a maybe 10-year-old kid. If you take the hat of a 10-year-old kid and if you show them this picture and say, I'm dedicating almost all of my resources to memory and storage, what should be my bottleneck? If you have a 10-year-old kid, please do that experiment, and you can report it back if you want. Probably they will tell you it's not what you're dedicating all of your resources to. And it's good to keep things honest. And maybe you can ask them next, okay, am I doing things right? If I'm dedicating almost all of my resources to memory and storage, and yet still memory and storage are my major bottlenecks, probably they will be nicely honest with you, and they will tell you, go design something else. So this is about designing something else. I think we should really take that. I mean, I can go through a lot of slides, but in the end, I will conclude with mindset change. Basically, today our mindsets are all processor-centric, and moving that to a much more data-centric and memory-centric mindset is the thing that we're going to talk about a lot more. So let's take the hat of a 10-year-old kid. Let's be honest with ourselves. How would we design our systems if we didn't have all of this baggage of, let's say, industry and processor-centric mindset, which is much more than industry, actually. It's really in all of our education system from the very, very beginning. We start with processor design, processor design, processor design, processor design, processor design. In a traditional course, you don't even get to memory. Is that the right thing to do? That's also good to ask, basically, if memory is the big bottleneck. Okay, anyway, I can keep philosophizing. Let's talk about data. This is data from Google. In their beautiful 2015 ISCA paper, they basically present the microarchitectural analysis of all of their data center workloads on a top-of-the-line processor at the time. You can see that most of the time, the processor is waiting for memory. These are mostly memory cycles. The processor is doing what it's supposed to do, finish instructions only 10 to 20% of the time. Okay, let's take the hat of a 10-year-old kid again. We're designing this processor to finish instructions. That's the only goal, really. Finish instructions as quickly as possible. High performance processing, right? and it's doing what it's supposed to do only 10 to 20% of the time. And the kid would say, you're doing things wrong. Hopefully. I believe in kids more than I believe in, let's say, anyway, politicians. Okay, so that was performance. Energy is much worse, basically. If you look at energy, we're wasting a lot of energy. And again, this is a nice picture from Bill Dell. You can find in the papers also. You can argue with the numbers, but numbers don't matter as much. The relative numbers matter. Essentially, if you look at this picture, a 64-bit double precision floating point operation is 20 picojoules. A memory access is 16 nanojoules. That's 800x. Okay, if you optimize things, you can get closer to 100x. And you can get maybe 100, 150x today. Not bad, but still huge, right? That's a big discrepancy. So we're moving data to basically, computation is cheap. Memory access is expensive, and there are good reasons for it because computation is scaled really well using logic technology scaling. Interconnects and memory did not scale very well over the course of 80 years. And they have become a much bigger bottleneck. And for the foreseeable future, they're going to become an even bigger bottleneck. So the question to ask is, does it really make sense to move the data to do very simple computation and keep moving the data back and forth? You would waste a lot of energy. Of course, this is an optimization problem, right? It's not a, let's say, dogma. You need to optimize things. And if your goal is to minimize energy, when does it make sense to actually move the data to the computation? And when does it make sense to actually not do that? Is the right question to ask. And if you do those calculations, there are a lot of papers that show that your locality needs to be very high to actually overcome or amortize the cost of energy of data movement, essentially. And you need to basically reuse a data element hundreds or thousands of times. Right? And how many applications do we have that reuses data elements hundreds of thousands of times? Not so many. Right? You could optimize things, but not so easy. Okay, so let's make things even worse. If you make the computation cheaper, a simpler arithmetic operation, the disparity increases to 6400x. And today, everybody wants to make the computation cheaper, right? We don't want 32-bit. We don't want floating point. We don't want 32-bit integer. We want 2-bit integer, 3-bit integer, maybe 4-bit integer, ideally 1-bit integer, right? That will actually reduce, increase this disparity. That reduces computation cost much more than it reduces data movement cost, actually. So 6400x. We're not even talking about storage yet. This is DRAM access. If you look at storage, multiply that by another 10x. So the numbers go crazy. And again, take the hat of a 10-year-old kid. I'm not going to talk about it more, but you can think about it. Okay, so we tried to quantify the effect of data movement on many workloads. Some of the works we did with Google. This is a little bit old right now, 70 years ago, but it's still one of the quantifications of real workloads on real systems. And we found out that on real workloads, on average use cases, not the worst case is much worse than this, but on average use cases, for example, if you're using video encoding and decoding, like YouTube, if you're using compression, decompression, if you're using Chrome browser, TensorFlow inference, which is essentially what we're using right now when we're actually doing a lot of this. Most of the system energy is spent on data movement, 60%. Now, if you actually go to accelerators, we repeated the study, again with Google, using edge machine learning accelerators, using edge TPU, and on proprietary Google models that are used in the field. And we found out that more than 90% of the total system energy is really spent on memory. Just to give you a quick glimpse, especially in large machine learning models used in edge devices, you can see that most of the energy is spent on DRAM and off-chip interconnect. Computation doesn't even, you cannot even see it from that far, at least with my eyes. But maybe you have better eyes than me. Okay, so basically, today we have a problem. And the fundamental problem is we're processing data far away from the data. And we don't have an option. Basically, we don't have the option to say, I want to process the data here versus here versus here. Because of that option is not available to us, we're really doing the worst case, if you will. Data is always moving to the processor, and you have to optimize for that. If you had the option to do computation, let's say everywhere, or at least some other places, other than processors, today we have a lot of places, but they're all processor-centric. CPUs, GPUs, FPGAs, whatever you pick, they're all processor-centric. But we want to actually enable that option. So basically, we want to enable computation with minimal data movement. And this requires computing where it makes sense, where data resides, where data is generated. And this leads to more data-centric architectures. And if you look at some system that could be in your pocket, we're actually restricting ourselves to do computation in this SRAM-dominated chip, very small fraction of it, again. Everything else is idle, doing nothing, other than serving the demands of this processor, right? So we would like to enable computation everywhere. This is easier said than done. There are multiple ways of thinking about it. The easier transition model is really treating memory as an accelerator. because we know how to design many, many accelerators, except they're all processor-centric. They're all sitting on the left side of the memory bus, if you look at this picture. Why not design some accelerators on the right side of the memory bus, meaning closer to memory, maybe inside memory? Okay. Even this, I would say that this is actually a shorter term. The longer term, we don't even have a central processing unit. Everything is an accelerator, and you actually program things in a distributed agent-based model, and everything can do computation. So it's a very distributed system. Today, we're not there yet. I mean, we're not even here yet. Yeah. So, okay, so even this model actually opens up a lot of questions. That's what makes this exciting. And that's what triggered us actually to hold these workshops so that we can have people from different communities interacting with each other, all the way from devices to algorithms. And there are many questions over here, because how do you design the compute-capable memory and controllers? That's a device problem as well as an architecture problem, actually. It really spans the lower part of here. How do you design the processor and communication units? How do you design the software and hardware interfaces to enable this sort of execution? How do you design the higher level of the stack, system software, compilers, and languages to take advantage of things and make it easier for people to adopt this? And how do you change your algorithms to fit what you've designed in the hardware level? Because some of the things that we will talk about is, for example, going to be very different from how we do computation in CPUs today. It could be block bitwise parallel, for example, and that requires new algorithm thinking. And my favorite is really the theoretical foundations, and I don't see anyone working on this, and I would encourage theoretically minded people to think about this. Because if you look at, how many people here have taken a computer science theory class? Algorithmic complexity? Probably a lot of people. Probably what you've done is big O notation, big theta notation, and you've probably studied it. You've tried to quantify in exams the algorithmic complexity of a given algorithm. And what you do in those things is really count operations, right? But maybe it doesn't matter. Maybe we're actually optimizing algorithms for the wrong target number of operations as opposed to data movement plus some sort of computation, right? So it's good to think about that, and I would encourage theoretically minded people to really develop a data-centric theory of computing. Okay, so we're going to talk a lot about processing in memory, and I should say that we're not the smartest kids on the block. There are a lot of people who were quite smart, starting from 1960s. If you know earlier papers, please let me know. This is the earliest paper that I could find. It's a beautiful paper. This proposes what I will call as processing near memory. Basically, you have logic, you have memory. You put logic closer and closer to memory. There are also other papers like Harold Stone. So this idea has been around for many, many years. For various reasons, it didn't get adopted. We can get into that, but we don't have a lot of time. So why is it interesting today? In my opinion, today we have nowhere to escape. We're really getting squeezed from both technology levels as well as the application levels. I've already given you a lot of the application higher level reasons why we need to minimize data movement. And also, I think there are also some, let's say, psychological or zeitgeist reasons, which is we need performance, energy, and sustainability all at the same time today. We don't want a trade-off between any of them. The days of I get 2% performance for 1% energy cost, it's gone. We don't want that sort of trade-off. We want to improve all three metrics. And we can actually improve all three metrics by minimizing data movement and changing the mindset. So, okay, I'm going to talk briefly. I have a lot of slides, but I'm going to talk briefly about this lower level part because we don't have a lot of talk. We don't have a lot of time. But basically, at the technology level, we're being pushed up also. We just had this DRAM security workshop, and there were a lot of DRAM folks over there, including some DRAM vendors. And they're actually having a lot of problems with technology like RowHammer, RowPress, and who knows what else will come next. And because of these issues, they're actually implementing controllers inside the DRAM. Basically, they're actually doing computation, some sort of computation, to manage DRAM. And if you already are paying some cost to do that sort of computation, why not pay a little bit more cost to get even higher benefit? Basically, don't just solve the technology scaling problems by having more intelligence in the memory to understand what's going on in memory and to make the memory better because the scaling is not going well. Do more. And emerging technologies can also enable more in this direction. So basically, we're kind of squeezed in the middle. And hopefully, I'll convince you in the rest of the talk. But I've already given you some examples. Any questions? Otherwise, I'd go jump into memory technology scaling. But I don't intend to cover this a lot. Otherwise, Alper will not be able to talk. But I want him to talk. Yeah. You still have time. I still have 38 minutes. But feel free to ask questions. Again, we don't need to cover everything. OK, technology scaling. So this is an area that's fascinating to me. When we first started doing work in 2010 or so in this area, we wanted to design like hardware to test memory, to understand some of these technology scaling issues. And this is one example, hardware. We have a laboratory, thanks to Ismail. He took all of these pictures. There's a little error over here. Yeah, maybe you can blur that out or something. Okay, but basically this is our laboratory for testing memory, and we intend to expand it so that we can discover new issues in memory. And these are some infrastructures that we've designed for different memory chips to understand memory. This is actually where we did a lot of the RowHammer work, which I will briefly talk about. And these are some early DRAM testing infrastructures that we designed. This is the earliest one, actually. And we open sourced it, and we'd be happy to help anyone who's interested. This is the older version of SoftMC. This is a newer version, DRAM Bender. And I think the goal here is to really understand what's going on in memory and to solve the problems. One of the things that we have worked a lot on is RowHammer problem. Very quickly, what is the problem? Essentially, if you keep activating a row, meaning applying Hall voltage to that word line to read some data that's in that row, and if you keep doing this repeatedly, activate, pre-charge, open, close, open, close, open, close, open, close, okay, like this, and this is legal in DRAM, it turns out physically adjacent bits in physically adjacent rows, some of them that are vulnerable, flip, meaning they lose their charge, they get corrupted. This should not be happening because you're not doing anything illegal in DRAM with this. You're actually just doing activation and pre-charge. And you can also internally reads and writes if you're interested. You can read the paper. This is old now. But basically, this should not be happening. You should not get bit flips in any part of memory while you're reading some other part. So this is a disturbance problem. And this is a technology scaling problem. And this has become much worse over many years. So initially, when we did the studies, there was a number of activations that you needed to do, 100,000 or the order of 100,000 or so, to induce a bit flip. As cells became smaller and closer to each other, because they induce more noise to each other at that level, we found out that over the course of 10 years in experimental data, there's a more than 100x reduction in the number of activations you need to do to induce a bit flip. So scaling problems will get much worse and worse. If you're interested, you can read our papers on the topic. And this became a security issue also because many people have shown that you can exploit this sort of bit flip that's happening to take over a system, read data that you don't have access to, break out a virtual machine, sandboxes. You can corrupt important data. If you're one of those people who only care about ML and AI, this should interest you perhaps. You can render ML inference useless. You can steal secret data like cryptography keys and ML model parameters. So it's very fascinating, I think. But the core of the problem is it's really a technology scaling problem. And the question is, how do we solve it? And this is getting worse. 2 years ago at ISCA, we presented the row press phenomenon. I'll very quickly talk about the phenomenon. In RowHammer, if you keep activating a row as frequently as possible. In row press, the idea is if you activate a row, but keep it active for a long amount of time, some amount of time, you induce bit flips in a much worse way. This is a different redisturbance phenomenon, and it turns out you need much fewer activations to induce a bit flip. So combining these two phenomena, actually, you get a lot more bit flips. And these are examples of two different scaling phenomena. If you're interested, you can read the papers. But why am I telling you this? Basically, solving these issues at the very low levels, device level, circuit level, people are working on it very hard, actually, and they're trying, is difficult, at least at the moment, unless you move to a new technology, which is costly, or unless you pay a lot of cost. So we've always argued that you need intelligence in the memory controllers to solve this problem. We call it system memory co-design. And this is a paper that I wrote like 12 years ago, invited to International Memory Workshop. More recently, and we argued basically that. You need intelligent controllers to solve these scaling issues. These scaling issues will get much, much worse. We need to have better system design to solve the problem. They invited me again 12 years later, and I basically said the same thing. But I said that it's getting much worse. So we had a lot more solutions, of course, over the course of 12 years. And so we keep arguing for the same thing. OK, I've also mentioned, we titled this work, Solving Memory's Computing Problem. There's a beautiful paper by Mark Horowitz that says computing's energy problem. I will argue that computing doesn't have an energy problem. The problem is there because of memory. If you actually get rid of the memory problem, you will save a whole lot of energy. And at that point, energy will become your problem, in my opinion. And because you would solve the memory's problem. So this is my fun, I think. Anyway, so OK, the good news is industry is listening. And actually, this is a paper written by S.K. Hynix in ISSCC 2023. And this is the paper where they acknowledge there's a RowHammer problem. And they actually provide some solutions to it. And the solution is essentially intelligent memory controllers inside the DRAM. And the idea is you have, next to each row, they add an activation counter. We had actually a beautiful discussion in the DRAM sec workshop. You can actually look at it. There are a lot of industry folks who attended the workshop, and they talked about the solution, this particular solution. It's all online, live streamed. Micron was there. Okay, basically the idea is next to each row, you have an activation counter. DRAM internally has a controller that counts the number of activations that happen to each row. And internally, if that activation counter is greater than some threshold that's not disclosed, it takes some action, some mitigating action to solve the problem, which is basically refreshing some rows or doing whatever, basically. They don't disclose a lot of it. But the high-level takeaway is, this is, in my opinion, maybe it's not the best solution, but it's a solution in the right direction, in the sense that now you have an intelligent controller trying to fix the issue, as opposed to either not fixing the issue or fixing the issue in some other way, let's say. Okay, and this was standardized by JEDEC. This is actually probably the largest change that has happened to DRAM in the last 20 years of DRAM's history. You can talk to Microsoft and Google folks about that, because that's their claim. I'm just quoting them, which is good, I think, because but it also shows you that these technology scaling problems are really causing a lot of churn, and they're causing the inclusion of intelligent controllers inside DRAM. So if you're willing to include this sort of controller inside your DRAM chip, and if you know the DRAM industry, maybe some of you don't know, but if you went to the DRAM industry 10 years ago, which we did, and if you told them you need to do this, this, this to solve this problem, they would have kicked you out of the room. I mean, they were nicer to us. They didn't kick us out of the room, but they didn't believe us. But today, 10 years later, they have intelligent controllers. If you're willing to do this, why not do more, right? Okay. Okay, there's always the question, of course, are the solutions good? So this is a solution. Is it a good solution to the problem you're trying to solve? Depends on the problem, I guess. Okay, sorry. If the problem is preventing access to whatever comes after this, well, you didn't solve the problem, right? So it's good to look at these solutions, and we have papers talking about this. DRAMsec actually had a lot of papers earlier this morning. If you're interested, it's a fascinating area. So there's a lot more to come in these technology scaling issues. Let me give you a very quick glimpse. Aging affects row hammer worse. You can read papers about this. More recently at HPCA, we found out that it's very, very difficult to prevent row hammer, because it's even very difficult to identify the number of activations you need to induce a bit flip. This changes randomly, unpredictably over time. And this actually requires an even more intelligent controller on the DRAM side. Okay, if you're interested, again, we have papers on this topic. You can say, okay, what about other memories? Other memories are even worse. I will not get into that in more detail, but if you look at emerging memory technologies, we have worked on different types of memory technologies for a number of years. People should be working on them. Don't be discouraged by the fact that Intel discontinued Optane. Academia should not care. People should be working on emerging technologies. I'm going to get to that, sorry, wait. But these emerging technologies have a lot of issues. And as they scale down to smaller nodes, they will have even more issues. And some of them off the bat have endurance issues that requires an intelligent controller immediately. So in my opinion, we have nowhere to escape. That's why we're building all of this infrastructure to understand memory even better. And I'd encourage people to build more infrastructure. You just need to provide the hardware today. You can download our source code, and you can actually do a lot of fascinating things. And the good news is people are listening, and there's a lot of sessions at HPCA, for example, ASPLOS, ISCA coming up on row hammer today. And there's more to come, and this is the DRAMsec papers that happened. Okay. You have a question? Optane? Yes. Yeah. Not just architecture, systems also. A lot of systems people stopped working on Optane. Yeah, yeah. Okay. Yeah.
Saying you're encouraging, looking at alternative memory technologies,
Yeah.
but nothing's
Yeah, yeah.
non-volatile data.
Yeah. Yeah. Yeah, I mean, yeah.
But is there a concrete application where there's a win-win-win-win?
Yeah, yeah. I think applications may come later. I think that's a very good question. But basically, we really need to understand the technology and its implication. And there's a lot of work actually that's going on in the device community that on emerging technologies. Maybe they don't compete with DRAM yet, but we really need to understand how they might potentially compete with existing technologies and what they can enable. No question about that. I think one of the issues with Optane was there was no, let's say, killer application that people were able to demonstrate. But again, I think I'm not convinced that that's enough of a reason to kill a research area. I think people should be more open-minded in research. Yeah. Okay, very good. Any other questions? No Rowhammer questions. You can ask some folks who attended DRAM Sec. There are a lot of people there. Okay. Okay, let me jump into processing in memory. I'm going to cover two types of processing in memory. And in my opinion, there are really only two types in terms of nature of processing in memory. I call it processing in memory. The terminology in this area is horrible. We tried to correct it, but it doesn't get corrected. When people called logic in memory in 1960s, I like that actually. They talk about logic and memory. They put logic near memory, actually. So that's why I call it processing near memory. So basically, processing near memory is you have logic, you have memory. Normally, these two things are designed completely differently from each other. Design flow is different. Design mindset is different. Even fabrication is different in some technologies. So logic and memory are separately designed. So processing near memory means put logic closer and closer and closer close to memory. Design them separately still, but put them as close as possible to each other to reduce the energy, reduce the data moment, basically. Energy and performance impact of data moment. You could put them, for example, in the logic layer of 3D stacked memory. You could put them next to each bank. You could put logic into next to each cell, right? That's a potential possibility. It could be disruptive, but it's still logic near memory. Processing using memory is completely different. Logic, memory, forget about logic. Assume that we don't have logic, we don't design logic. You use memory to do computation. And any memory has some fundamental operational principles, usually analog operational principles, that enable computation. This is fascinating because this is, I think, more fundamental in the sense that you can reduce energy efficiency much more. You can reduce energy much more. But there's a trade-off between these two. If you actually design logic separately, you can have much more complicated logic, potentially. Where here you can gain more energy efficiency and you can exploit very large bit-level parallelism. In the end, I think these need to be combined. And I think it's fascinating to work on both of those. I'm going to go through processing near memory relatively quickly, and then introduce processing using memory, and then we're going to conclude. Or should we have a choice? Which one do you want to talk about? This is actually instructive. Who wants to talk about processing near memory? Shorter term, more industry relevant today, perhaps? Okay. Who wants to talk about processing using memory? Okay, usually I get more hands, and this didn't change my mind, but it's more of a balance over here. Who has no opinion? Okay. Who doesn't care? They want to do processor-centric research. Okay. Okay, you're in the wrong workshop, but we're going to convince you. Yeah. Okay. So I'm going to talk about near memory because I saw enough hands on near memory, but I'll go through it relatively quickly. So basically, near memory means put logic near memory. And this is happening today. They're actually real chips, DRAM chips, modified to do computation. UpMem, for example, is the first company. Unfortunately, they're bought right now, so maybe you don't have availability to the system. Talk to us if you don't have availability, because we should be getting some systems from them, maybe their latest system. Yes, they're purchased recently. Is it public? It should be public. I think I've gotten a lot of emails, but I can tell you later, yeah, because I don't know for sure if it's public. But if you've been working with them and you don't have access to their servers, talk to us. Okay, but basically what they did was in the DRAM chip, they put processors next to memory. And it's a very general purpose processor, multiple instruction, multiple data. We analyzed this a lot, actually, and we looked at the positives and negatives. So you can find, I'm not going to talk about this. I think this is near term, which is very interesting. But you can actually run real applications on this. There's actually work in this area. There are also other systems that are not as easily available from Samsung, SK Hynix, and Oliveira, where they modify the DRAM chips. And again, near each bank, they put specialized units to accelerate machine learning or recommendation systems. And also, you can do other things like putting a buffer chip, which is an FPGA, in a module of a lot of memory to accelerate recommendation systems, for example. Okay, so this is near memory processing. It's also enabled more easily by interconnects or interfaces like CXL, Compute Express Link. You can actually offload a lot of computation to somewhere other than the processor today. So very, very interesting. Clearly, that you can see papers and claims by memory manufacturers. And I think it's great that memory manufacturers are working on things like this. We should actually not think of them as memory manufacturers. And my message going into the future is they should be doing memory plus computing as opposed to just memory. We should break that barrier between memory and computation. Okay, let me give you some example results from our own research. When we first started looking into this around 2012 or so, we were very interested in 3D stack technologies. At that time, 3D stack technologies were not that mature. And you had basically, what is 3D stacking? You have a logic layer underneath memory layers, and you can connect the logic layer with memory layers with high density, high bandwidth, low latency, and reasonably low energy interconnects through silicon vias, for example. And how small you can make that interconnect enables higher bandwidth and potentially lower latency. So at the time we were doing this, those true silicon vias were large. Today we have other, let's say, integration technologies like hybrid bonding that increases the number of interconnects you can put by 2 orders of magnitude, for example, compared to true silicon vias, which makes it much better. So believing in the technology is what we did essentially, and we wanted to explore what this technology would enable if we could actually do computation near memory using this technology. And this is what we designed. Again, I will not go into the details of it in much detail, but I still like this work a lot. We call this Tesseract. You have this 3D stacked memory plus logic. In the logic layer, we put a parallel array of in-order cores. And our goal was to accelerate graph computation, but you could actually use it to accelerate anything, in my opinion. The idea is to offload the graph computation from the host to a distributed array of these cubes, because memory is large. The amount of memory you need for graph processing is large, and one of these cubes is not enough. So you really need actually a huge array of this. Then you can do computation inside these in-order cores. And the idea is to minimize, it's still exploit locality, minimize the movement of things across these cubes and maximize the computation that's done inside each logic layer. And to be able to do that, we basically move the functions to the data as opposed to data to the functions. We want to minimize data movement, and that turns out to be a better choice. And to be able to do that, the way programming is done, you do remote function calls. Essentially, when a processor needs to invoke a function on some data, it sends a function call to another processor that houses that data. The programming model is very similar to how distributed systems are programmed today, essentially. Okay, there are a lot more other details that I will not cover over here. But if you do all of this, the end system that you get is different from what is available at the time and mostly today. Basically here, the existing systems have a processor and memory dichotomy. Processor and memory are designed separately, as you can see. And you have a big bandwidth bottleneck. So the bandwidth at the time was the highest bandwidth at 640 gigabytes per second. Tesseract didn't look like an existing system because you have memory and logic near memory processing coupled, and you have a distributed system of near memory processors, essentially. If you squint at it, this looks like how GPUs are designed today, except they're not really near memory, right? They're close to memory. They're nearer to memory than this system because they have HBM, but they don't do exactly what we do. So we should have looked at machine learning at the time. Missed opportunity. But the key is basically, even at the time, you get 8 terabytes per second, which is much larger than what you have available to all of these cores. And the performance benefits are commensurate. Basically, we showed significant performance improvement, more than 10x, and significant energy reductions, more than 8x. And later works, this is, we're talking about 2015, later works actually reduced the energy to maybe 100x by optimizing things, and increased the performance to 100x. So this is not a trade-off. You get performance on the order of 100x, you get energy reduction on the order of 100x. Right? Some people like thinking about EDP. If you do a sloppy job, you can just multiply those two, and you get 100 times 100. Okay, this is the paper. The paper was rejected twice before it was accepted. But folks decided to include it in the 50 years of ISCA special issue, so maybe we're redeemed a little bit. So if you're rejected, don't worry. Believe in your ideas and just take the comments and do better, let's say. Okay, I'm not going to talk about some of these things, but if you actually take it up to a higher level, you can design the ISA and also algorithms completely differently to take advantage of processing in memory and processing using memory, and you get even higher benefits. Let me quickly talk about this. I mentioned this work that we did with Google on accelerating machine learning. So we were very interested in different applications. We actually have a lot of work on different applications. This is actually one of the interesting things because we did together with Google, and we looked at commercial products that they have. And what we found is across all of the different neural networks that they had at the time, there's a huge variation in terms of arithmetic intensity of the neural network layer, and also a huge variation in terms of parameter footprint. For example, some of the layers are very good for processing, and they don't require a lot of memory. They basically do 10,000 of computations for each byte that they fetch. Some of the other layers, especially from LSTMs and transducers, they're exactly the opposite if you look at it. They require a lot of memory. Their parameter footprint is large. and their arithmetic intensity is very low. So most of the time, the data that they bring, they're not working on. You can optimize this with compilers, etc. There are clearly research that you can do in that area, but getting this arithmetic intensity higher is very difficult in general. So we also looked at, for example, variation in terms of layer characteristics within a single network, and you can see that multiply and accumulate instructions vary a lot, and arithmetic intensity also varies a lot across different layers. Basically, we wanted to design an accelerator that could cater to these very highly varying characteristics. So today, people design accelerators monolithically. This is changing, I think. Well, at the time, definitely monolithically. And this monolithic accelerator, this poor accelerator, needs to execute everything, right? And it's trying to cater to both compute-centric parts and memory-centric parts. Our idea was basically, why not design, let's say, different accelerators, 3 accelerators in this particular incarnation. One of them is processor-centric, very similar to this one, but probably much leaner. Actually, it is much leaner. And 2 of them are memory-centric. They're in the logic layer of 3D stacked DRAM, and they cater to different types of data flows. Okay? And the difficulty now is pushed into the runtime layer, which needs to identify the layer characteristics and decide what layer needs to be scheduled where. But the interesting thing is you can actually reduce the hardware cost, overall hardware cost. These 3 accelerators designed together have a lower hardware cost than this monolithic accelerator. Okay. But the complexity is high, of course, right? There's a lot more complexity over here. Okay, so you need to identify the layer characteristics dynamically or statically. And if you do things, at least to some level of detail, you can do much better than this, in my opinion. But in the paper, we want to demonstrate a proof of concept. You can reduce the energy consumption by 3x, and you can also improve throughput by 3x. Again, these are at the same time. Okay, that's the paper. There's a lot more examples that I'm not going to talk about. You can accelerate different workloads. I mentioned genomics. Genomics is actually fascinating to me because the data sets are huge. Computations are not that expensive, depending on what you want to do. But in some cases, computations are quite expensive also, because neural networks exist in genomics also. So we looked at accelerating things. And more recently, this was ISCA 2024, last year, we wanted to look at huge data sets. And if you want to really deal with huge data sets, there's no way you're going to do it cost efficiently inside memory. You have to move to storage. And we're doing a lot of storage, in-storage processing, to actually do this cost efficiently. In my opinion, going forward, we need to move further and further into storage. If you look at the storage system, we have a very weird, again, 10-year-old hat. We have a very weird way of designing systems. As a 10-year-old kid, I cannot make sense of it. We have a processor, we have memory, and then we have a processor, and then memory and storage. This is the storage system. It's a system by itself. We have a system within a system, right? That should cause some thinking, perhaps. I think there's a lot of inefficiency we have in our systems, and probably a 10-year-old kid would solve it. Okay, anyway, I'm joking. But basically, there's a lot more. If you're interested, you can look at our paper that keeps growing. Geraldo is reminded that he'll need to look at the new version. This became almost 100 pages in the recent incarnation. But if you have feedback on this paper, we'd be happy to take it. Okay, let me quickly talk about 2 works, since some people only care about LLMs. They don't listen to me at all. Maybe neural networks, but neural networks are out of fashion today, right? It's all about LLMs. Who cares about neural networks? That was like last 5 years, maybe. Okay, we have been looking at LLMs. This is 2 works that we published at ASPLOS, Pappy and Cent. Very quickly, the principles are very similar. Basically, if you want to accelerate a large LLM model, let's say, there are portions that need to be executed in a high-performance GPU. There are portions that need to be executed close to memory. And this work identifies which portion needs to be executed where, and it designs a system. In this particular case, we have a high-performance GPU in these high processing units over here. And fully connected layers that are very compute-intensive get scheduled over there. Fully connected layers that are actually more memory-intensive get scheduled to this near-bank memory system. We call it FC PIM. And there's a lot of computational capability next to each bank, because fully connected layers tend to be highly intensive in terms of computation. But attention layers, they actually have a very different requirement. So we design another, let's say, processing near memory architecture for it that is connected through. Basically, we disaggregate the memory because it can be very large. KV caches can be very large. And we don't need a lot of, let's say, computational capability next to each bank, because attention layers tend to have let's say, very low arithmetic intensity. So that's the idea, basically. This is one design. I believe it can be improved. There could be a lot more over here, and you get significant speed ups and energy efficiency increases compared to best prior works. In this other work that we did together with Vitu's group, we were a little bit more aggressive, and our goal was to actually get rid of GPUs as much as possible. And we were able to get rid of GPUs while also achieving higher throughput, higher, let's say, performance, and also lower hardware cost. I'm not going to talk about that, so you can take a look at it, the paper. So it's good to, I think, examine alternative architectures that can be much better than, let's say, existing accelerator-based systems. And I think they need to be data-centric. It's very hard to, in my opinion, overcome, let's say, the performance and efficiency of GPUs today without being data-centric. Okay, any questions? Okay, yes. Well, your question is, what is the difference between accelerator and processing near memory? So processing near memory is a concept. Accelerator is a particular way of accelerating some mechanism, right? Processing near memory doesn't need to be an accelerator. Also, it can be completely a system by itself, right? All you do is processing near memory. You just need to make sure everything executes there. Does that make sense? So in this particular case, we're actually offloading some computations, accelerating some computations over here, but you can actually have a complete processor over here. This is just an accelerator implementation of processing near memory. Hopefully that answers your question. Like, for example, if you have UpMem system, that's a complete processor. It's a multiple instruction, multiple data. Maybe it has a lot of deficiencies, etc. But you could design a complete processor near memory. You could run an operating system on it. That's processing near memory with a complete processor, right? It doesn't exist yet, but the concept is beyond an accelerator. Yes?
In the processing model, if we take a multi-rate state that there is some power for the logic, there's some power for transfer, and there's some power for memory.
Yeah.
We still have the memory and logic power. And we get rid of interface.
Yeah.
I don't know the share of each of those components.
Yeah. This.
But actually, two questions. Do you have in any of your publication anywhere that discusses the share? And sometimes I see something like 10 times higher energy efficiency. I don't mean in your work, everywhere.
Yeah.
And I wonder that if we remove the interconnect power, we will get 10 times more energy efficiency, because everything seems like a traditional accelerator. Read memory, transfer, processing, right back.
Yeah.
Now, read memory, not transfer, because and the process, do the process.
Yeah.
So my question is that, how big is the impact of the interconnect?
There's some things in papers. Maybe Geraldo can point you to some of them. But I think I would argue that it's not just the interconnect, right? What you're doing here is you're adding units over here. So you're exploiting the bank level parallelism, the bandwidth, high bandwidth available inside the memory. So you're reducing the interconnect, yes, but you're also exploiting the high bandwidth that's available inside the memory. So you're gaining benefits, not just from the reduction of the data moment, but also the exploiting of the parallelism. Does that make sense? And in fact, in the more extreme cases, we'd like to exploit that parallelism as much as possible. Today, you're bottlenecked by the interconnect, right? That's why we cannot exploit that parallelism as much. The interconnect that you have between processor and memory, high bandwidth memory alleviates that a little bit, but still, it's a big bottleneck. You're also reducing latency because you're closer. Yeah.
I'm trying to understand how it helps to having that 3.4 times higher energy efficiency.
3.4 times is not that bad, but basically you're reducing the execution time also, right? You're saving energy because of the execution times. Okay.
I'm not trying to challenge. I'm
trying
to understand. So
I would recommend doing studies on your own. You can do it today. The best way to understand is getting your hands dirty and doing these studies, and you will see. And we have a lot of tools. I will get to them maybe, but yeah. Think about it. You're reducing data movement, exploiting parallelism, reducing latency, And all of those are helping energy also. Don't think just performance, right? Reducing latency helps energy. We've done a lot of work on reducing latency. That actually helps energy. In fact, in my opinion, I could give this talk on latency. We have a very bad way of designing systems in terms of latency because latency impacts energy also, right? So think about it. No, not just static power. You actually reduce dynamic power by reducing latency, right? You're not moving data that long, right? It's not, okay, you could argue interconnect power, yes. Yeah, okay. I wouldn't say just talk to me, because whatever I'm going to say, I don't believe is going to convince you. Get your hands dirty. You'll see a lot of these results and even higher, perhaps. And that's my recommendation to everyone, actually. If you don't believe these results, everything is available online, actually, almost everything that we do. You can go, get your hands dirty, replicate it. If you found some discrepancy, then come and talk to us, and we'll correct it. Okay? All right. That's why we release everything. There's nothing we're hiding. In fact, Geraldo is going to talk about some of the infrastructures that he has built, right? Compilers, etc. It's all open. We have data. We believe in the data. But that's how it is, right? Okay, very quickly, I think. Processing near DRAM while using memory. I think I want to give some time for Alper also, but this is a fascinating area, so I have to talk about it. But basically, processing using memory is a completely different approach. You have logic and you have memory. Forget about logic. Now we're going to exploit the analog operational properties of memory. And this is going to lead to even higher energy efficiency improvements, more than 10x, 100x, 1000x. And hopefully you'll be convinced, but I don't think you'll be convinced. You can still download the source code and do the experiments yourself. Okay, but basically what we can do is we can natively support a lot of operations, the bulk bitwise copying, initialization, and or not majority, true random number generation, and more complex computation using lookup tables. Most of these at low cost, not all of these. Lookup tables can be expensive sometimes. And we're going to exploit the analog computation capability of DRAM. And the key idea is if you activate multiple rows in sequence or in parallel, this performs computation. And the fascinating thing, the really fascinating part, at least for me, is you can do this even in commodity off-the-shelf chips. Basically, I'm going to show you some circuit results based on circuit characteristics. We believe that this is doable. But some of these functions exist even in existing chips without modifying the chips. So some of these results were fascinating to DRAM manufacturers also, because they didn't know that their chips were capable like this. Yeah. Okay, so let's quickly go over this. Copying and initialization, this is actually a big bottleneck in many applications. And these two function calls, memmem and memcopy, in Google, in their 2015 paper, they said that they occupy 5% of all of their execution cycles in their data center. Now, this is a big number. 5% is a big number, especially for two function calls only. And this is not on the data moment. And in their paper, they said, actually, our paper was published before their paper. They said that approaches like what I'm going to describe soon are actually a good approaches to investigate going into the future to reduce the data moment overhead of copy. So how do we do the copy today? If you want to copy, let's say, large scale, you can do this at small scale also. There are mechanisms. I'm not going to talk about the larger copies, like page level copies. If you want to copy this white page to this gray page, today you have to bring everything to the cache, do the write, actually the register file, do the write, and then write back the data eventually. So basically you need to move 12 kilobytes of data in the end to do a copy of 4 kilobytes. Again, let's take the hat of a 10-year-old. You give this picture to the 10-year-old, explain what you're doing today, and explain that also this white part and the gray part are very close to each other. They will be, again, honest with you, and they will say, why don't you just do this, stupid? Okay, sorry, I had to add the stupid, but that's because of someone else added stupid. They blame Bill Clinton. Like he said, it's the economy stupid, and we called it the memory stupid, thanks to Bill Clinton. Okay, but basically, a 10-year-old kid probably would come up with this. And again, I'll challenge you, if you have a kid, try it. Okay, that's the idea, basically. We'd like to do this. And again, you can argue against this many, many ways, but you cannot argue that this is the intuitive way of doing it. Okay, this low latency, low bandwidth, no cache pollution, no unwanted data moment. So I'm going to show you a mechanism of how to do this and reducing latency by about 11x, reducing DRAM energy by about 70x or so. And the idea is very simple. If you look at the DRAM subarray, internally it looks like this. We first activate the source row, which brings the data into the row buffer, which is sense amplifiers. Data is very strong over here. This all exists in DRAM today. And based on chart sharing principles, if you activate the destination row, deactivating the source row, you connect the sense amplifiers to the destination row, and the data gets captured into the destination cells. That's the idea. By doing 2 consecutive activates, you can reduce the latency and reduce the energy significantly and do this completely in parallel. Okay, so basically it's negligible hardware cost. And if you're interested in doing other types of copies across banks, across subarrays, we have a lot of solutions to that. I'm not going to talk about that. This is the fastest way. So this is RowClone. We showed that this is actually good for many applications. But let's talk about computation. If you want to do computation, you need to do multiple row activation. The idea is these are 3 cells, A, B, C. These are 3 capacitors in DRAM, and these are 3 access transistors. And I'm showing you only 1 bit, basically. And this is the bit line, and this is the sense amplifier, and this is the other end of the bit line. Now, if you had the primitive to do concurrent row activation, if you concurrently activate these 3 rows, what happens is, based on chart sharing principles, in a perfect circuit, if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. And that's a bitwise majority function. Basically, it's bitwise majority, which is actually computation, as you can see. And if you take C and set it to 1, you get OR of A and B. If you set C to 0, you get the end of A and B. So the good thing is you get bitwise OR, bitwise AND, bitwise majority. What's missing for Boolean completeness is bitwise NOT. But if you actually activate 1 row, you actually have the complement of that cell on the other end of the sense amplifier. In this paper, we propose a expensive mechanism of actually connecting this to the subarray. There needs to be more work in this area to actually connect the, let's say, do the inversion, at least this way, right? Okay, I'll leave it at that. But if you're able to do inversion also, you can get significant performance improvements. These are end-to-end performance improvements when you map a database application. Databases are actually sometimes written to maximize bitwise operations, bitweaving database, for example. You get significant performance improvements and energy improvements also. So there are many other applications that can actually take advantage of this. As long as you can actually rethink your algorithm and write things to be bulk bitwise, you get a lot of benefits. We are working on, for example, Alper is going to talk about homomorphic encryption in a different way. But you can actually do homomorphic encryption in a bulk bitwise manner using this sort of substrate. Stay tuned for that for later. Okay, that's the paper. I'm going to skip some of these because Geraldo is going to talk about these, and we don't have a whole lot of time. But you can make this more general purpose. You can actually implement any operation this way. And with the right framework, with the right tool chain, you can actually, for example, you can do convolution. And you can come up with a hardware circuit for convolution, and we can optimize it through electronic design automation and generate a microprogram for convolution and invoke it using compilers or the programmers from the program, and that gets executed in the memory controller. So this is a, let's say, way of adopting this sort of execution model while still maintaining sequential execution on the, let's say, program side. Okay. I'll go through this quickly because Geraldo is going to talk about it, as I said. So you get significant performance energy improvements. Energy improvements will increase. That's SIMDR. More recently, again, Geraldo will talk about this in more detail, but one of the issues with this sort of bulk bitwise operation is the granularity. If the granularity is very large, because DRAM granularity is very large, 8 kilobytes, let's say, or 4 kilobytes. If you had a fine-grained DRAM where you can enable individual mats, then you can actually reduce the granularity to, let's say, 512 bits. And you can do this computation on 512 bits at a time. And this is good because you don't need to waste a whole row to do the computation. And you can also do other things on the other mats. So now you enable a multiple instruction, multiple data model. And to be able to do that, you need to have a fine-grained DRAM where you can enable individual mats. Okay, I will not talk about this. Geraldo, you can take over with that one. But this also eases programmability because now we can actually target existing compilers that work on 512-bit granularity, which is the AVX granularity, if you think about it. And Geraldo did this for LLVM. And you could actually take that and actually compile applications much more easily for this substrate. Okay, I will not talk about this. Again, Geraldo will talk. And we see significant performance and energy efficiency improvements. And the main reason for these large improvements, and we verified this many, many times, we're looking at the entire chip, right? The entire DRAM is doing computation across all of its cells. So you're really utilizing the entire DRAM to do the computation in a very highly parallel manner. You're reducing data movement completely. if you look at a GPU or a CPU, there's a lot of stuff over there that's not participating in the computation. Control overheads, etc. We got rid of a lot of the control overheads. People actually get rid of control overheads in other things like systolic arrays, etc. And they get significant performance and energy improvements. But here, every bit is really doing computation, if you think about it. OK. OK, let me quickly talk about this. There will be more people who will talk about it. But I think, to me, the most fascinating part is, you could say, what are you smoking earlier, right? Everything. We're not smoking anything. Well, basically, the circuit level, the chart sharing principles show that this is doable. The difficulty is, of course, in the details in general. That's why we wanted to also examine, can we do this in real DRAM chips? We're actually inspired by work from Princeton. They had this compute DRAM paper where they verified that operations like I described, RowClone and Ambit, are actually doable in existing DRAM chips by violating the timing parameters. So based on that inspiration, we built this infrastructure, PyDRAM, which is essentially an end-to-end processing in DRAM system where you have an FPGA. Inside the FPGA, you have a RISC-V processor. You can execute an application on the RISC-V processor. And when you get to a page copy, this RISC-V, that page copy gets offloaded to the memory controller, which violates the timing parameters between activate to activate. And in existing DRAM chips, it turns out you can do this RowClone quite reliably. I'm going to show you some results. And this end-to-end system, you can actually examine many different applications. So in real systems, we measure significant throughput improvements, for example. This is a real benchmark, micro benchmark. You can run it on real FPGA. Again, if you don't believe us, you can go and download the source code. This is all open online. You just need to provide your own FPGA. Sorry, we don't supply that. We're not that rich. I think Xilinx or AMD should supply that, probably. Not me. They don't even supply it to us. OK. But basically, you can get real performance improvements. OK, that's PyDRAM. More recently, Ismail, who will talk about some of these things. You'll talk about some of these, right? Later today? Maybe. OK, really quickly. He has shown that on real DRAM chips, you can get many operations. This is a summary. For example, you can copy one row into up to 31 other rows with almost perfect success rate. These are real results. Doing multiple row activation. Basically, you copy, you open one row, and then that brings the data into the sense amplifiers. In quick succession, you do a multiple row activation that opens many rows in the same subarray. And that copies the data in the sense amplifiers to the many rows. That's the idea. And fascinatingly, this large copy, like copying one row to 31 other rows, is almost perfect, which is fascinating to me. Right? DRAM chip, OK, just to put things in context, we're not modifying anything in DRAM. DRAM is not designed for this purpose. We're just abusing DRAM, violating timing parameters, showing that you can actually do these operations that we envisioned, let's say, 10 years ago. And in a much more, let's say, more complicated operations. We've also shown that you can do the NOT operation and NAND, OR, and NOR operations. I've already said this, so I'm going to skip this. I'm going to skip NOT. I'm going to talk about NAND, NOR, and OR, because these are the most difficult parts, in my opinion. So basically, these are two cells on a subarray, A and B. They're connected to one end of the sense amplifier. In DRAM, this is the open bit line architecture. On the other end of the sense amplifier, there's another subarray that's connected over here. To reduce cost, DRAM manufacturers do this optimization. But this enables computation capability. Now, assume that we are able to concurrently activate all these four cells. That's called multiple row activation. And you can do this by violating timing parameters today because of the hierarchical design of the row decoder, existing DRAM chips. You just need to change the memory controller. Now, at the circuit level, what does this mean? Based on chart sharing principles, there's a sense amplifier. The result, it will compute the result that compares the average voltage of A and B to average voltage of X and Y. So if the average voltage A and B is greater than average voltage X and Y, you will get a charge state over here, which is 1, let's say, and you get the discharge state over here. OK, now let's take a look at what we can do. This is one thing you can do. If you actually, let's call this the reference subarray, 2 cells over here. Let's call this the compute subarray. And we're going to compute a function of X and Y by setting values in the reference subarray. Assume that you set values in the reference subarray to VDD and VDD over 2. And you can do that in DRAM chips today. If you want to know how, there's, again, another paper from the Princeton group that describes how, or Ismail can tell you how. This is still fascinating to me that you can set the cell to VDD over 2, but you can do it. Now, the average voltage here is 3 VDD over 4. If you want to get a 1 or charge state over here, the average voltage here should be VDD. Right? And when do you get VDD? When both X and Y are VDD. Meaning that the function you compute here evaluates to 1 over here only if X and Y are 1. Otherwise, it's 0. And we know what that function is. It's an AND function, right? It's an AND function in the compute subarray. It's a NAND function in the reference subarray. Okay, hopefully that makes sense. And you could actually come up with NOR and OR. And you could actually have many inputs with this. So this is fascinating. This is, again, circuit principles. I haven't shown you results, but real results. You can actually do this in real DRAM chips. Okay, and you can find that in the paper. Now let me give you some real results. We tested a lot of chips. This is data from, again, real chips. On average, copying. If you do a multi-row copy, depending on the number of destination rows, you get some reliability, which is success rate. And you can see that it's almost 100%, which is interesting. So maybe you can almost use it in real systems if you abuse the DRAM timing parameters. And NAND, OR, and NOR are not as good because, again, there's a lot of variation. There are a lot of reasons why you get errors. But they're not that bad either. In this particular case, for example, with 16 input operands, you get almost more than 94% success rate. Again, maybe it's not good enough to do real applications, but our goal is not to do real applications. The sole purpose, in my opinion, of this study, in fact, Ismail wanted to write a paper saying that, oh, we actually, he still thinks about that, saying that, oh, we actually accelerate real applications. I told him, don't do it. Use this as a real prototype to show the potential of DRAM. Right? This is actually showing the potential of DRAM, capability of DRAM. Right? Maybe someone will come up with applications that will actually accelerate this. So this is a challenge to many people over here. Can you use real DRAM to actually accelerate really big applications in the presence of these error rates? I don't believe that. You can prove me wrong. Okay, Ismail didn't prove me wrong yet. But he's discovered many other things. That's the good part. Okay, there are a lot of other things we can do with commodity memories, but I'm going to skip these. True random number generation is fascinating. These are real chip results from real memories by violating the timing parameters. You can read them. Okay, I'm going to skip this. You can do a lot of these things in flash memory. This is a work that we have done on flash memory, on real flash chips. Again, you can see these bulk bitwise operations. And more recently at ASPLOS, we've used those bulk bitwise operations in flash to accelerate homomorphic encryption, which is a fascinating application in my opinion, which needs to be a lot more energy efficient than high performance. And we're working on how to do it in DRAM. Okay, that brings me to the end. There's a lot more in our survey paper and some other papers. I think the most difficult part of everything that I described, including near memory processing, is adoption. Because you can build any hardware in the end. The difficult part is getting it adopted. And there are many, many adoption issues over here. Geraldo will talk about some of these adoption issues. We have papers, for example. Geraldo's thesis was actually on this topic. In the end, we really need to solve these adoption issues. And they're not easy. We can start small. We can incorporate smaller ideas more easily. But in the end, I believe we need to have a much more memory-centric mindset. Because if you think about it, you can push back on everything that I said, because existing systems don't do it that way, right? If you look at existing systems, even the data mapping is not designed for this purpose. Data mapping is designed in a processor-centric manner. When we first start our courses, we're processor-centric. It's very hard to get out of that mindset, right? In the end, it's really all about the mindset, in my opinion. Once you change your mindset, you can enable a lot of things. Okay, this is Geraldo's thesis. So he finally finished. And he has a nice thesis that covers across the stack, as you can see, programming models, tools, and systems. And he's going to talk about some of them. Okay, I'm going to conclude. I've said a lot of these things. Basically, I've highlighted recent advances, especially in processing in DRAM. This can lead to orders of magnitude energy and performance improvements. And I believe we're just uncovering things. There's more to come. And again, what's fascinating to me is you can do these even in unmodified DRAM chips. I believe memory should be designed as a combined memory plus storage substrate as opposed to an inactive storage substrate. And this requires actually even bigger mindset change because the memory industry doesn't even work that way. The design mindset and flow should change. But I believe the future is bright and we need more people working in these areas. We really need to do research and design across the stack with a proper mindset and infrastructure shift. Maybe this will be my last-ish slide. I like the slides because I know nothing about what happens here. I took a lot of neuropsychology and cognitive psychology courses, and a lot of people are trying to discover what happens. But one thing we're really sure doesn't happen is the dichotomy between memory, communication, and computation. We don't quite understand how this is combined in the substrate, and I don't believe existing neural networks are anywhere close to modeling this. But the principle is combined memory, computation, and communication, and we're not doing that in our systems today. So hopefully we'll change it. Okay, I think I'm done. I'm happy to take more questions. And we're not terribly late, so that's good. Yes, please.
Do you think that this will be an even bigger push to say memory, since now memory is going to be even farther away from your compute nodes, like using CXL interconnect, connecting to a memory expansion card, is you have even more links.
Yeah, that's a good question. I think CXL, I like the good, let me tell you about the good part of the CXL. I think the good part is it's a flexible, relatively flexible interface. It can enable many things, including offloading computation. So in that sense, I think it'll be good for processing near memory. The bad part is the latency. I agree that that latency could be a good motivator for doing things closer to memory. Hopefully that latency will still go away. That doesn't reduce the motivation for doing processing near memory, I think. Does that make sense? So I think CXL is a good enabler for pushing computation somewhere other than the processor. But hopefully the latency will not be that bad, because that if the latency is large, then it disables some like fine-grained communication, for example, that might need to happen. But latency could be a motivator also, sure. Yes, please. Processing using memory on what, sorry? Computer. Oh, okay, that's a great question. Yeah. So I think they're the same thing. Some people just call it SIM, compute in memory. We use it processing. We call processing using memory. I think because compute in memory to me means nothing. Yeah. No. Forget about compute in memory. Compute in memory, basically, people usually use computing in memory for example, analog matrix vector multiplication in MRAM, right? Which is processing using memory in our terminology. You're using the memory's operational properties to do computation. So I don't like the term compute in memory. Compute in memory means nothing to me. That's why we try to fix the terminology. No one wants to fix the terminology, fine. But compute in memory, the way people traditionally use it is the same as what we use, processing using memory. People called it logic in memory. What's the difference of logic in memory and compute in memory? Those are the 1960s, right? They were right, actually. Logic in memory. I would call it logic near memory, right? So we use processing in memory as a general way of defining doing something near or close using memory. Yeah. Okay. Yes, please. Yeah. Mm-hmm.
Basically speaking, I think memory is good at moving data from the cells to the ports.
Yes.
But not moving data around the cells.
Yes. Yeah, outstanding comment, I think. I agree with you. We need more. So there's another inspiration that we can get from this thing over here. There's a lot of connectivity here. If you look at memory today, connectivity is very low. It's really designed to move from the cells to outside, right? But we really need, actually, we have some work that tries to move data between cells much faster, between subarrays, for example, low-cost interlinked subarrays. I think there definitely needs to be a lot more work to do better connectivity inside the memory arrays so that we can actually do better computation also, right? Because it's not just about computation. If you don't have the interconnects to do communication inside the memory, it's going to be very tough. You're back to the same problem, right? You move the data far away, and you need to aggregate it somewhere, yeah. But that's actually great. I think that's why we're calling for really more thinking. Okay, I go back. Yeah, this one. Essentially, we need to have not an inactive storage substrate. The way memory is designed today is it's a storage substrate. You only get the data out, right? But if you're designing memory and computation together as a computation substrate, you really need to solve the interconnects inside the memory also. And I think emerging technologies will help. I should also add some more things. It's very difficult to do with the DRAM mindset today because it's very cost sensitive. Fabrication is not easy. You have very few metal layers. So adding communication with very few metal layers is difficult. But if you actually have 3D stacking and a logic layer, you can actually do a lot more connectivity in that logic layer. We had this work, for example, on network on memory. Inside the logic layer, we have a lot of connectivity so that we can connect different banks together And those things are very good for computation. There's more work also from Kai's, John Kim's group, for example. They actually do a lot of interesting work in this area. That's right, yes. PIMNet, for example. Right? Yeah. Okay. Yes.
I have one. First of all, so I was recently reading some papers about ReRAM-based accelerator, right? And yeah, storing and doing computation at the same time, there are a lot of benefits, especially the reduction in power. So energy storage. So the problem was the lifespan, right, of the ReRAM cells, because after some writes they become faulty. So what is the trend? Do you know what is the trend coming here? Because it seems to solve the problem, right? These accelerators, but short lifespan.
Yeah, so endurance basically. Like endurance. Yeah. Essentially, that's one of the reasons why I flashed the phase change memory, because it suffers from the same problem. I think it's very difficult to solve some of the endurance problems in these technologies, because when you do the writes, you're really destroying part of the substrate, and as a result, it's very difficult to solve. That's why you need intelligent controllers, and computation is also limited. We have the same issue in Flash also, actually. That's why read-intensive workloads are better fit. But once you start doing a lot of writes, or if your computation requires a lot of writes inside the cells, then you have a problem, basically. I don't have a good solution, sorry. I think it's good that people are investigating it. That's one of the reasons why I actually kind of said what I said about Optane. It's not just about Optane, but those technologies are actually good, but I'm not sure if their usage models will be very general purpose. Sure. Yes, please. Oh. Yeah, certainly, yes. That's a very good question also. Basically, I didn't talk about NVM as much, but we could also look at NVM. So in DRAM, for example, it's very difficult to do things other than bulk bitwise operations. Of course, someone will hopefully discover some other things. We don't know, or you need to change the substrate a little bit. But in NVM, like, for example, RRAM or MRAM or even PCM, so in all of those, you can do all of these operations that I described, actually. People have shown that, and you get a lot of benefits. But you can also do analog matrix vector multiplication, for example. That I don't know how to do in DRAM today. So there's a big advantage in that sense. But of course, NVM still need to prove themselves. They're not there yet. And when I talk about NVM, in this case, I'm talking about emerging NVM. There's also Flash, which is NVM, but it's charge-based, and that is also difficult to do matrix vector multiplication. Okay, yes. Yeah, absolutely. No question about that. I think you need to do computation everywhere. And if you look at a chip today, it's mostly SRAM. We're really designing SRAM chips. And today, most of it is, that SRAM is useless. Well, useless in the sense that useless for computation, right? So if you can actually do large-scale computation in SRAM, you can get benefits. And there are applications that fit in SRAM, for example. And there are application portions that can be accelerated in SRAM. So in the end, I think we need to enable computation everywhere, and we need to design a way of scheduling computation to different parts. And there are clearly a lot of works on SRAM also. In my opinion, I like those works, no question about that. I feel it's a bit easier, because it's easier to fabricate, easier to demonstrate, etc. And industry should be looking at that. There are a lot of startups, etc. I think the harder problem is really how to enable very large-scale memories, low-cost memories like DRAM and Flash to do the computation, because there are many data sets that are just not going to fit in SRAM.
Question?
Okay. You can do concurrent questioning. Okay. Who wants to go? Okay, great question. Ismail is going to tackle that. He has an ISCA paper talking about it. Yeah, later today also, but you can read our ISCA paper, which is also on archive. But basically, very quickly, processing using memory especially makes RowHammer much worse. And he's going to show you some real results from real chips. Yeah. Of course, because that one of the solution for the RowHammer as
wonder to know, is it still enough to protect such a rowhammer attack for PIM?
Yeah.
Take the component
Yeah.
do you think should we design or stronger PIM architecture to prevent such danger?
Yeah. I mean, that's a good question. I think when you're designing PIM, you need to be aware of all of these issues, and you need to quantify them, and you need to solve them. But in the end, I think the solution direction is not going to change. You need to solve rowhammer independently, whether or not you have PIM. PIM makes the problem worse, and maybe the solutions need to be a little bit different. And Ismail will mention that. But we need to develop maybe better solutions than what we have today. So there's an opportunity for research in that area as well. You're welcome. Are we done? Or?
Get your concurrent question.
Okay. Yeah. Yeah. Yeah, I mean, that's a good question also. I think in the end, people will try to optimize things. But history, at least for the last 50 years, tells us that it's very hard to get rid of memory bottleneck. Maybe you can do some things and reduce it, but over time, people will develop applications where the memory will still become a bottleneck. It's always this sort of game, right? And there are enough applications that it's very hard to solve these issues in general. That's why we have huge memories today, right? Otherwise, we would have gotten rid of the capacity also, right? So I think these issues will continue to, let's say, haunt us. Even though local improvements will be made in some algorithms, I believe they will be short-lived. In the end, you're dealing with a lot of data, and you're going to be bottlenecked by data. And there are also other considerations when you develop new algorithms, right? Maybe energy is not going to be good, even though you solve the performance problem somewhat. You see what I mean? So I think you will need to develop more memory-centric solutions, no question about that. We had another question, though, that I missed. I was going to answer that. Yeah, you. Okay, I was going to say something related to that, but I missed it. Okay. Oh, yeah, what's memory-intensive? Oh, okay, yeah, that's okay, yeah, thanks, yes. So basically, is PIM only good for memory-intensive things? That's a great question. And if it's near memory processing, maybe. But if you look at processing using memory, it's a completely different computational paradigm, right? If you have your DRAM chip doing computation in every one of its cells concurrently, that's very highly parallel processing also, right? I wouldn't call that about memory intensity anymore, right? If you're able to distribute your computation to every single cell, let's say, maybe it's not just for memory intensive operations, it's for some definition of memory intensive, right? You still need a lot of memory, probably, to do the computation. And this is one way of scaling your computation in parallel, right? You could argue, okay, I can scale the same computation in parallel with across many, many processors. All of them are doing, let's say, vector operations, etc. I agree. You could do that, assuming the memory is not a bottleneck, assuming your goal is parallelism. But that'll be more expensive, in my opinion. The reason is you're using much more expensive technology, SRAM, right? To get the same capacity ratio at the same level of parallelism, I think more memory-centric computing using some dense technology is probably better in terms of cost. And I think that needs to be proven. What I just said needs to be proven. But we actually have some results that show that, for example, if you do in the Megis paper in last ISCA, if you do metagenomics inside Flash, you can do a lot of your operations inside Flash, and you can get rid of a lot of the DRAM in your system. So your cost, you can improve your cost efficiency as well. So these are some of the trade-offs that don't get questioned. But I challenge the research community to question things, right? We're building all of these processor-centric systems, and maybe they are very good for computation, but at what cost is the part that we forget, because we already paid that cost, and we keep paying that cost, and that cost seems easy. In the memory-centric computing system, yes, you pay a huge cost initially, but the gain may be much better overall. So we need a better way of quantifying the cost of our systems today also. You're welcome.
Thank the speaker.
Okay, thank you. Okay, Altair's next.
Not producing, like,
Okay, maybe I'll introduce him.
okay,
Yeah.
perfect. So I don't butcher his
Oh, are you
his
gonna
last
use
name.
your? Okay, okay, yeah. Oh, oh, you're gonna use your computer?
Yeah.
Go, yeah, go ahead. Or you can connect to Zoom. It's easier.
No, the internet doesn't.
Oh, internet doesn't work. Okay, yeah. Oh, yeah, sorry. Okay. All right. I think we take whatever.
Seriously, half an hour?
Half an hour is fine. Yeah, yeah, no problem. Yeah, we're usually flexible in these times.
Okay.
Do you need to be somewhere?
Light is there.
Yeah, yeah, it's not very good. I had that's why I stayed over there.
I want to see people done.
Yeah, yeah. I think if you stay over there, unless you want, no, you cannot do it. You have to stay over there or over here. Oh, good luck then. Close your eyes.
Can I walk?
Maybe you can go down. I don't know if you need to have a clicker though.
Zoom, because he's going to use his computer,
Okay.
and then you're not
Internet
going to be
doesn't
able to. His internet's not working.
Okay. EduROM is not work. Maybe you can log into EduROM with him.
I can try to log in his computer to EduROM,
Yeah, yeah.
or I don't have a
Huh.
flash stick here. Around 50
Well,
people.
online there's a lot actually. You're missing the online. I think why don't you log in his computer like EduROM? Do you have EduROM? Did you try EduROM? Okay. But still, you should be able to EduROM, I think. Because you probably don't have EduROM at IBM, right?
The internet is shady. Like
Yeah,
I
yeah.
can do the Zoom, but it's just.
Yeah, we can do it, I think. It's which network?
Okay.
Which network are you
I
on?
mean, if there's any another strong network, I can use.
Yeah, EduROM. Are you able to connect to that?
Oh no.
Yeah, that's much stronger. Just use that. Yeah.
Let me do that.
You can connect it for him because we're going to have an invited talk by Alper, Dr. Alper Büyüktosunoğlu. He doesn't have the longest last name, I know, but he probably has the most difficult one. Alper.
My last name has no hash collision.
No hash collision.
See a last name like this from my our
Oh, okay. That's a good one. Yeah. Okay, Alper is a principal research scientist at the Efficient and Resilient Systems Department at IBM T.J. Watson Research Center. He's done a lot of work on the IBM Z processor and IBM Power Systems. Okay, you're going to talk about that today? Okay. Okay, next time we'll invite you. No, I want you to talk about memory-centric systems. Oh, no, I know you can, yes. Alper can talk about anything, but today he is choosing to talk about fully homomorphic encryption near DRAM. Yeah. No, it's not just a fit, because they had work at HPCA on this topic, which is a nice paper, and we invited him to actually give a talk at ICS, and he said, I don't want to go to Salt Lake City. I want to be in Japan. So he decided to come to Japan for this workshop. He's going to talk about this work. But Alper has been around for a while. Okay. He got his PhD from University of Rochester a number of years ago, at least 25 years. Yeah. Am I wrong? Am I correct? Okay, more than 20 for sure. And he's done a lot of work. He's not a foreigner to the computer architecture community. You can see him in a lot of conferences. And if you want to get honest feedback on your work, just ask him. I'd recommend that, yes. Yeah. Yes. You can ask him or Andre, who is sitting in the back. Andre also will give you honest feedback. Sorry to put you on the spot, but that's true, I think. Okay, I guess I could keep going. Alper has been a member of Hall of Fame of Micro, HPCA, IBM Master Inventor, IEEE Fellow, and a member of the IBM Academy of Technology. Let's welcome him, but the computer is not welcoming him. So, is it all good? Okay, great. Network works better than the other networks, so. Academia, Edu-ROM connectivity. We don't get a lot of money, but we get perks.
Where's the microphone?
Oh, okay, okay. Yeah. No, guys, the point of this presentation is to give you some high level points of what we did. Actually, our guys did. Yeah, one second. Almost there, guys. How is that now? All good? What? Yeah, tell me. Yeah,
Do you need the notes?
Not really, but it's okay to keep it if you want.
It's the opposite actually. If you
not
to remove it,
Notes are good for me.
perfect. Everything's perfect. If
Okay.
you don't need them.
Thank you, sir. Thank you. Okay, we are good. Yeah, she's very concerned. She's looking at me. So, yeah, I mean, we actually Yongmu is the guy who did a lot of the work with Apurva and Subankar. Those are the sort of the lead guys. I'll tell you where my most contribution is throughout the talk. So the talk is about near DRAM acceleration for compiler-generated fully homomorphic encryption applications. The first time they told me about FHE, I had no idea what that is. I still don't have any idea what that is. I mean, I have some idea, but not to the extent that I would like to know, right? So what I want to do is, before I get into the near DRAM part of things, I'm going to give you a little bit detail about FHE, okay? All right. So I don't know if anybody is familiar with FHE here. Okay, so you're familiar, you're familiar, you're familiar. Okay, good. So there's a good crowd. Okay. So in case there's an FHE question, we have 4 people. You can ask those questions to those guys. All right. So let's get rolling. And the guys picked the thing Fendi, okay? We even when we were in Las Vegas, we went to the store Fendi. It's a very branded thing without the H. We took a picture. But that's that friend of mine is very, they love this Fendi thing. But anyway, so I'm going to get into a little bit of background. So there's a lot of privacy preserving solutions, okay? FHE is the holy grail of all of it, all right? So I don't know how many of you are familiar. There is Secure Enclave, right? Secure Enclave is a hardware-based isolation technology, right? I mean, it creates basically a protected region of memory within a processor, all right? So it ensures that data code within the enclave they are all inaccessible to the outside processes, all right? Even the OS or in the hypervisor, right? So I think a lot of you know about this. Once you're inside the enclave, data is decrypted. This is very important. Once you're in the enclave, data is decrypted, all right? And then computed, and then the results again get encrypted when it's going out, all right? So in that sense, it creates a potential vulnerability, right? I mean, because if the enclave security is compromised due to hardware bugs or side channels, you are vulnerable, all right? So by the way, throughout my presentation, I'll harp on 5 things for you to remember, because it's very hard to remember everything I'm telling you. So I will kind of, at the end of a slide, I'll tell you, hey, remember this thing from this slide, all right? So that you guys all can wake up, right? You're all jet lagged. It's like killing me right now. So fully homomorphic encryption addresses these shortcomings of this, what we call the secure enclave, by enabling computation on the encrypted data, all right? Only thing to remember from this slides, you can do computation on encrypted data, period, all right? Forget about everything else I say, but I will say it anyway. So this eliminates the risk of data exposure, right? Because once you're computing on the encrypted data, it eliminates all the risk of data exposure, even if the computation environment is compromised. But you guys are gonna see this in a while. The trade-off is that FHE is extremely intensive, expensive, and slower compared to enclave-based computation. All right? And then there are other alternatives: secure multi-party computation, federated learning, differential privacy, oblivious RAM, a lot of other things out there. But FHE is the holy grail. All right? So let's move to the next slide. Any question on this? I'm letting this sink. All right? This is just the background. We're going to come to the near DRAM part, right? Those interested in near DRAM, we'll get there. All right. So this is sort of showing you what I verbally said. You have a message. All right. I don't know if I can point here. You have a message. You go through this encode, encrypt. This encode does some entity transformation and all those type of things. You go through the encrypt. You have a ciphertext, and then you couple that with some public key, some evaluation key, some secret key, and then you do computation on the encrypted data. You can't do everything on the encrypted data, but you can do a lot of things, such as addition, multiplication, key switching, preliminarization. We call it key. I mean, they are sort of synonymous, rotation, those type of things. And then once you're done on the encrypted data, computation on the encrypted data, you basically decrypt, right? Ciphertext, decode, and you got the result back. So while this is happening, right, nobody can access, nobody can do anything. All right? However, there is a tons of math that converts that message to the ciphertext. All right? And at the end of the day, that message blows up, right? And that ciphertext becomes a gigantic data. All right? And I'm going to tell you, if you're really interested, what that ciphertext is going to look like. And in this talk, we're going to talk mostly about the CKKS scheme. It's a public key-based FHE scheme that can encrypt complex numbers, but there are other FHE schemes as well, BGB and others, right? Okay. All right. So this is the data from someone. I think it was published in the IEEE Access. You want to do ResNet 20, inference for a CFAR10 data set on CPU. In an unencrypted system, it's going to take this long. CKKS takes 10,000 whatever, 60 seconds. 2 million times slower. Whoa. Right? Bad. So I'm going to get into now more and more details of the CKKS-based FHE. Like you showed in the picture, FHE is a public key scheme, right? It's a secret key and a public key are generated. And then public key is used for encryption. It can be shared, right? But the private key is used for decryption and must be kept secret. Okay? And FHE is based on ring learning with errors, hardness problem. It's really a crypto thing. Again, I have some backup slides. If somebody's really interested in, we can get into that. But this is known to be as hard as whatever worst case lattice problems. And these lattice problems are currently secure actually against attacks from quantum computers. So this is, from the security point of view, it's very hard to break it. All right? And it allows you to do homomorphically encrypted addition, multiplication, and rotations, right? And the thing to remember from here, CKKS allows you to operate on underlying set of fixed point values, all right? That kind of distinguishes itself from the BGV. Okay? Everything so far so good? You guys sort of getting into it, like high-level concepts? I see some heads shaking. Some people are sleeping, which is fine. Some eyes just opened. All right, good. Let's get into more. Okay. When they show me this FHE, I said, can you show me the data structure? I mean, I used to be good at math. In high school, they even, I was in a team, we were getting ready for the Math Olympics. I couldn't get selected at the end. I was really good at math, actually. But after that, I dropped, 40 years ago, my life became just multiplication and addition. That's all you need in computer architecture, right? But this math is pretty fascinating, okay? Whoever came up with making sure this thing checks out is, brilliant people. And whoever make this FHE work is brilliant. Who used to be an IBM research guy, actually, Craig Gentry, all right? So what happens is you have a plain text message, a vector of complex numbers, all right? So at the end of all that conversion that I was talking about, it comes out as two polynomials. Everybody knows polynomials, right? Two big polynomials. But when I say big, it's big, all right? So basically, we are talking about a pair of two polynomials in some, domain, a0 to an minus 1. And then in this case, the number of coefficients is 2 to the power 17, all right? And then the value of these things are qubit width, which is about, for example, if you want to satisfy 128-bit security level, we are talking about 2305 bits, all right? 2,300 bits. I want to let this sink in. We are talking about a gigantic data, okay? Anybody interested why these two polynomials happen? I can jump to a backup slide if there is a quick interest. I see some heads shaking. All right, let me show that really quick. This is actually, I took it from one of my crypto guys who happened to be here, and he's gonna describe some of these things tomorrow in another workshop. Under the hood, the reason these two polynomials happen is this. You have a secret key SX. By the way, I'm describing BGV, but CKKS kind of follows it. You have a secret key SX, right? To encrypt a message, what you do is you choose a random polynomial AX at random from some field, right? And then you choose a random Gaussian error. And then you create a B, another polynomial B. Remember in the previous slide, I was showing you A and B, right? You create another polynomial, which is B. And BX is nothing but AX multiplied by SX, right? Message itself, right? That we want to encrypt. And then the error term, okay? And then when you do a decryption, basically what you're doing is the reverse operation, right? But what happened is now that little m that little message becomes this gigantic A and B polynomial. All right? Okay. Some people are on the phone. I'm going back. So that was sort of the context. Okay, so oops. Again, went from there. You want to do what? Man, you guys are too sophisticated for me.
Just clicking here.
This one?
This dot. And
You don't
high
want
presenter view.
on this one?
You're not using memory-centric computers.
No, I don't use it. Okay. Now the thing is, how do you handle this large queue? Okay, so we went from this little m, gigantic two polynomials A and B, and then we have this huge large queue. All right. So how do you handle large queue in digital circuits? Any idea? I'm asking non-FHE guys. Even FHE guys, how do you handle? Second row, blue shirt. How do you handle large queue?
This side.
Okay. Anybody? Anybody? Yes. How do you do that? Exactly. Bingo. All right. So you do residue number system, Math 101. Yeah. Okay. You do an RNS decomposition. All right. Really large queue can be break it down to the machine word size, right? So now the QI will fit in 32 64-bit. All right. I'm going back to really calculus. If you want to have Q30, you break it down Q12, Q23, Q35, W6, so the 29 can become 124, 11 can become 121. And then if you want to do operation on it, what you're doing is really very simplified version of it. Okay? This is important. The reason it's important is by doing this, what happens is now the operation obviously grow quite a bit, but the bits that you're operating on become very manageable. Okay? And now we introduce this term called limps. So you had two polynomials, remember? We have A and B. Now what happened is polynomial grew because of that large queue, and now you have limps. All right? I see some shaking hands. All right? Everybody with me? This is going to be important. That's why I'm kind of start emphasizing on this a little bit. Because when I start describing the architecture part of it, I'm going to come back to this quite a bit. So you have the two polynomial, and coefficient is similar, but the data grew, right? You have many limps. The expansion factor is actually, there's a simple math on that. It's really, that equation, and then you got 2 multiplied by L plus 1. If the n is 2 to the power 16, right? And then L is 31, expansion is, we are talking about 64x. The data becomes suddenly like, if you were doing 0.25 megabyte, now you're operating on 16 megabyte of data. Okay? Another background. A lot of you guys took FFT, right? So what happens is, when you take two polynomials, right, in crypto whatever system, and if you want to multiply them, okay, we're talking about a gigantic multiplication. I mean, you can take a naive approach and just multiply those two things, but what you're going to have is an n squared growth, right? But we know from past in FFT and digital Fourier transform, you can reduce to n log n. Anybody knows how we get that n log n? Any algorithm, anything that pops in someone's mind? Right here. Cooley-Tukey. Okay? So Cooley-Tukey are the guys. By the way, Cooley used to be an IBM research guy. Obviously, he passed away. We just celebrated actually the 50th anniversary of that algorithm. Discovered this thing. So basically what you do is, think of it, Oops, sorry. And forget about the entity part, but what they discovered was that multiplication can bring it down to n log n through this sort of this radix structure, right? And entity does a similar thing. Entity is nothing but FFT to reduce that, when you take two polynomials and multiply, to reduce the complexity from n squared to, order of n. So what you do is you do an inverse NTT and take an entity transformation of two polynomials, right? You get AX multiplied by BX in n log n. Okay? Does that make sense? Or is it too confusing? You still cannot relate to, I see some, this is very confusing. I see some heads like, this is really confusing. I'm going to tie it back to the near memory soon, but this really needs to happen. Otherwise, it will be really hard to follow what the architecture proposal, okay? So far, let's remember things. FHE, I can do computation on encryption. We got that, right? The data that I'm doing computation on FHE is two large polynomials, all right? I think I see heads shaking. Okay, good. Two polynomials, really large polynomials. So there are schemes to reduce the complexity of the operation on those two polynomials. Especially multiplying two really large polynomials is extremely hard, okay? When you add, it's linear. I mean, a lot of crypto operation linear is fine, right? You can add and subtract, that's no problem. But multiplication is really complicated, right? So there are things out there like I showed NTT and that Chinese remainder theorem or residue number theorem to reduce the complexity. But when you do this Chinese theorem, right, or the residue number system, what happens is you expand the data, correct? All right, so these are the 4 or 5 things to remember. I don't want to overly confuse, right? So at the end of the day, what we got is summarization of what I said. Message become a ciphertext with two polynomials, and the two polynomials really in the RNS system really grow, right? We are talking about large growth. So this is sort of the summary. We are talking about CKKS. It can do an approximate arithmetic computation on the complex numbers. It's a perfect fit for machine learning type of applications. And then, again, we are talking about 2 to 4 orders of magnitude slower than the unencrypted computation. Okay, now, be patient with me. One more background slide. The good thing about what I described, from an architect point of view, there is levels of data parallelism in this and data interaction, okay? So it operates actually, when we start calculating, when we start doing computation on FHE, what happens is you have many parallelism built inside it. One of them, you might guess by now, is the limp-wise parallel, right? When you're doing an NTT, what you're doing is the data is interacted across the coefficient of a single limb, and the limbs are independent. Does that make sense? All right. So you're doing this NTT, for example. There is data interaction across the coefficients of a single limb, but the limbs are independent. Remember that limbs are independent. All right. We're going to come back when you guys see the architecture. Everything is going to fit hopefully in your head. The second one, coefficient-wise parallel. Forget about this base conversion. I'm going to come back to that. So basically here, there is data interaction across the limbs of a single coefficient. Okay? So what happens is the coefficients are independent. So that's what we call this coefficient-wise parallel. And then here, the element-wise parallel, which is going to come into this modular ed. Each limb of coefficient, all right, is independent, and there is no data interaction. So that's the element-wise parallel. All right. This slide is a killer slide. This slide is important. Once you figure this one out, once you understand this, then you guys can architect your own thing. I mean, we architect a version of it, all right, which is extremely complex. And then there's the ciphertext-wise parallel, right? So what happens is there's also parallel rotations, right? So there is data interaction within only a single ciphertext, but the multiple ciphertext can be operated independently. All right. So what did we talk about? Let's quickly recap. Limp-wise, element-wise, coefficient-wise, and ciphertext-wise. All right? 4 different parallelism. All right, let's confuse you more. This is not an easy thing. When you do multiply, it's a dyadic multiplication. It's not an easy. You take a 2 polynomial, right? And now you're multiplying them. It's not like a simple multiply, right? Because what happens is Yeah. When you multiply, the number of polynomials grow up, right? Because we started with one polynomial and now you're multiplying, there are like suddenly 4 polynomials. So what happens is you have to reduce the number of polynomials, and that's why you have to go through this key switch operation. And that key switch operation is not a simple operation. It involves a bunch of other things, mode up and inner product, mode down, and all that. And within that mode up, actually, you have to get out of the entity domain. Remember, we convert our data to entity. Like we used to do this in college days. We used to go to the Fourier mode, right? Do computation and then come back. So we did a similar thing. We went to entity mode, right? We were doing computation. Bomb. Suddenly, we are doing a multiplication. We have to get out of it. You have to do a base conversion, and then again do an entity, and then do this whole thing together for that mode up. Okay? And then the story doesn't stop here. So after you do key switch, you have to go through a rescale. And after that rescale, what happens is actually you're losing one of the limps. This is going to be important because once you lose a limp, you have to do a bootstrap operation because you can't do so many multiplications back to back. All right? Did I lose everybody? Yeah, pretty much I lost everybody, or there's still one or two kind of saying, hey, I'm kind of following, or? Yeah, my hope is on that 5th row. He seemed to follow a bit, right? Yeah, I'm kind of counting on that. So let's remember, 4 different of parallelism, right? You can go back and read when you go back to, you can remember this and then go back and read. 4 different of parallelism, right? But what happens is, within an operation, within a multiply operation, I kind of emphasize on the multiply. Multiply is hard. There's a bunch of other steps that you have to do, and because of those bunch of other steps, we have to define a bunch of other operations. All right? At least remember that much. So, summary, parallelism, and this, right? Now let's exploit these and design a architecture. All right? Let's see if that makes sense to you guys. This slide everybody should follow. Even their sleeping ones should wake up. There's a bunch of FHE accelerators out there. It's been published like, I don't know. I have this background slide, like 20 of them, right? I was telling my guys, if you want to publish any FHE work, you have to compare against those 20. All right, that's the name of the game. But they are deficient, right? First of all, when you look at a lot of these things, they are handcrafted workloads. A lot of the FHE workloads that the folks run out, until our work was sort of handcrafted workloads. And then they are less configurable, scalable, and then, they do an ASIC design. They have this gigantic SRAM, right? And then LU and NOC and those type of things, ASIC design. There's tremendous amount of on-off-chip memory interfaces. And then you have this gigantic SRAM because you want to hold all the data in the SRAM, right? It's easy to access and bring it back and forth. Okay? Oh, what a great idea. Let's do a new design. Let's first of all use compiler-generated workloads. None of this handcrafted work. I'm talking about IBM, real, use case, actual customer type of workloads. These are compiler-generated. You can't just do a handcraft. All right? If you don't like FHE, if you don't care, or if you want to get into this area, and if you want to use real workload, this is a good paper, actually, from that point of view. It has a lot of real workloads, and I think our guys open source it. Okay? They are highly configurable, and these are larger workload graph and many parallel nodes. But obviously, there's more pressure on the on-chip memory interfaces, right? And there's a lot of spills and feeds on the SRAM. Now we need a new solution. Again, slide to remember, what we are proposing is locate the compute units directly on the DRAM die, large on-die DRAM capacity, eliminate off-chip data transfer burden, and then use the DRAM internal bandwidth, higher DRAM internal bandwidth. This is very important, actually. A lot of people miss that point. When you do a DRAM computation in DRAM, you get a large internal bandwidth, right? Most people don't realize that. And to the best of our knowledge, this is actually when these guys published, it was the first FHE accelerator that does large-scale real-world compiled workloads. All right? Many contributions. This is where my contribution is, I will say mostly. I'll get into the Singleton. Singleton is my favorite. Singleton-based fold and permute for NTT on NDP. We did pipeline parallelism for bootstrapping, area power efficient Montgomery. I don't think I'm going to talk about it. Subarray parallelism, how we utilize that. I think our guys cite your, forgetting his name, Kim's paper. SELP, exactly. Who said SELP? Oh, okay, yeah, okay. You said, okay, good. No, Multiro, very good. No, I forgot the name. And then large scale real-world compiled workloads. And then we are using IBM HE layers from FHE. We have this big, actually, crypto group in IBM Haifa in Israel. And those are the guys actually who are doing a lot of this crypto work. They are hardcore theoretical guys that we operate together. Okay. All right. You just came in right time. This is the slide. These guys are smart. They skip all the FHE stuff. They don't need to know anything. You just came in right time. Okay, just take a seat. Take a seat. You guys, perfect timing, man. All right. Whoever is sleeping, they should just wake up for this slide, okay? And then you can go back to sleep. I told you this limp business will come at you. So this is the proposal. All right. Our guy said, let's take a proposed HBM-based design. This is quite far-fetched. Nobody's going to produce this anytime soon, but this is just a research, right? Sometimes we do this kind of stuff at IBM Research. I don't do Z all the time. But it's like really real. Okay, perfect. Yeah.
I think IBM decided you should do Z all the time.
Yeah, I think so. Okay. Each ciphertext goes to a different layer in HBM. Intuitive, makes sense. I don't think anybody will argue. Every die has a tile group. You can, what do they name it? A, B, C, D, whatever, right? And what an idea. We can map the limbs. Remember I told you the limbs to each tile group. It makes a lot of sense. Okay. If someone else says, hey, Alper, you should not map it to each tile group, we can discuss. All right. And then within the tile group, you have left banks, right banks. And then that's where our, this is our network, whatever, fixed permutation network. I'm going to describe this a little bit. Each of the element, remember the element-wise parallelism goes to right and left bank, okay? And then we have our CU array, which is the computational unit array. Because at the end of the day, you have to do computation, right? You can't just store the data. And that compute unit in itself has a lot of novelty in it. I'm not going to get into it. But it has some built-in ALUs and swap operations and those type of things. And then these guys, by the way, did the due diligence. They designed this network all the way, floor planned it, and everything. All right, just to put some real numbers to it. So what we are doing is, now, remember that parallelism I talked about it? We're just doing a hierarchical mapping of that parallelism into this substrate, right? HBM substrate. So I will let this sink a little bit. Anybody, any questions? Yeah, go ahead.
Do you need some extra logic for doing computations like on HBM when you try to utilize 2.5D and you want to parallelize at that level? Do you need extra logic for operations already at each slice?
Yes, I'll get into that a little bit. So you need the CU array. You got that, right? So CU array is the extra logic that you have to add. That's our computational unit. And this permute network is now different, at least within the tile, within the single die, right? You're with me. So that part is there. But we're not going to stop there. We're going to do even more logic within the banks. I'm going to get into that, if that's what you're asking.
Yeah. Because tile group is already HBM chip. It's not on a slice, or is it on a slice?
No, it's on the slice. So it's on a die.
Okay.
It's a die, right?
Oh, okay.
It's a die. Now, this tile is not your, father's, mother's, whatever tile. So, yeah. Yeah. Okay, good. Okay. Now, Singleton. Woof. If you do NTT on this tile group, the Kulituki, which is n log n, which is great, right? What happens is this happens. So you start on the left bank, right? You start on the right bank. So the left goes to right, right, through the CU array. And then next one, right goes to left. Okay? This is how just the nature of the computation, right? And then vice versa. You finish this Kulituki, right? The NTT. What happens is what you need is an all-to-all permutation network. All right? And between the left and the right banks. You see how inefficient it is? So basically, it's really hard to implement such a thing with, number of metal layers you get in an HBM. And a lot of people don't realize also, you have always limited number of metal layers in DRAM. Right? It's not like in our processor when we design it, I have, 18 metal layers, 20. Oh, it's beautiful. Everybody has a metal layer. In DRAM world, you only have 3 or 4 metal layers. You have to deal with that. Okay? And this is where I said to my guys, there is this thing called Singleton. That was my main contribution. They said, what is Singleton? I said, everybody should know about Singleton. I learned this in college. So Singleton lets you do n log n. A lot of people don't know. N log n. Forget about what I'm describing, actually. Go and read this paper. It's beautiful. Like, if you want to do FFT, you want to learn about Singleton, like, he's my sort of hero. So Singleton said, I'm going to do a 16-point. Example is 16-point. What it does is identical permutation over all the stages. It's beautiful. You see? Look at this permutation and look at this one. Identical. This is what he worked on in 1969. Identical permutation. You know why this is important? Anybody could guess?
I think it makes communication more easier, yeah, because data.
Exactly. It's here. I just need a simple fixed permutation network between left and right. Remember, I was going right, I was going left, but the network was like all over the place. This is fixed.
There is no switching on the hardware layer, so it's way simpler.
Yeah, exactly. Very simple. However, you have to fold this NDP. The NDP has to fold this along the inputs, as it's hard to process all of them at once, right? That's another thing. So Singleton is good, but you still have to do an extra step. You have to do fold and permute. And this is where, I was very intrigued. So it's like folding a paper, all right? You take a paper, you fold it. Same thing, you're going to fold it. So you take, 16-point Singleton, you fold it again, you permute the rows, and then fold it, fold it, fold it. So what happens is now you are maintaining Singleton geometry while you're folding this arbitrary endpoint entity into arbitrary less point of entities. This is another contribution in our paper, actually. All right, this is again important because, again, this makes the hardware very simple. So basically what happens is with this fold and permute algorithm, you can take any endpoint entity with a fixed permute network. Remember, first we said, hey, let's use Singleton, get a fixed permute network. But we didn't stop there because you need to do arbitrarily large n, right? When you do this, whatever FHE operations. Now this fold business can still use that fixed network. You guys with me? I have a fixed network, but now I can do arbitrarily large n. All right? All right, let's get to bootstrapping. This is one of the things, it's very confusing. I don't know, how am I doing in time? Around 5:10? Yeah. So remember at some point, I don't know, 7, 8 slides ago, I said we created limps and we did polynomial multiplication. And during that polynomial multiplication, remember what happened? I lost one of the limps. Remember I told you? Nobody remembers. Somebody remembers. Shaking hands, heads. Good. That losing limp is a bad thing. Because when you do multiply, if you do successive multiplies of polynomials, and if you keep losing limps, what's going to happen? You're going to run out of coefficients, right? It's not going to work. For example, your limp is 30, let's say. You multiply it 30 times, and you run out of all the limbs. So that's why they do bootstrapping. And this is the thing, another IBM research guy who actually invented the fully homomorphic encryption, Craig Gantry, invented this thing. All right? And this, unfortunately, this bootstrap operation is a complex operation, all right, in its nature. And it involves a lot of rotation, a lot of multiplication, addition, and rescale, and those type of things to get the limp back. And what we did in our proposal was we used pipeline parallelism for bootstrapping using the DRAM dice. Okay? So that was another thing. If you do a fully parallel mapping, unfortunately, if you do just a blind mapping, right, what's going to happen is it's going to suffer from the die-to-die synchronization. Remember, I was mapping these things on the each die. If you do this wrongly, then you're going to end up, ending up doing a lot of die-to-die synchronization. So instead, what we propose is we did a pipeline parallel mapping. All right. So what we did was this for the bootstrap operation, the real world compiled workloads have many parallel bootstrapping nodes. And now this could be pipeline on across different dies. So this bubbly thing is these operations you see, right? And I put it on each die. Okay. I probably lost everybody. Is that the case? Probably. Okay, good. So I think the only thing you should remember here is then this paper did something about bootstrap. All right. If I lost everybody, at least that part you will remember, right? But this is important. I can emphasize this thing. This bootstrap is extremely heavy math, and very what do you call it, math hungry work, right? And you really need to parallelize this when you do this NDP kind of computation across dies. And that parallelization is not a straightforward thing, and that's one of the things that this paper contributed. All right. Okay, another one. This is while we are doing this, we also propose a modulus format, some Montgomery multiplier, special multiplier. If anybody's interested, we can get into that. There was apparently another guy who did this math. I don't know, he was from Sabancı or somewhere. So our proposal was much better than any one of the things out there. This is part of the, just another contribution. Nothing to do with DRAM, but. Okay. SELP. All right. So what we had to do is, now, remember the subarray thing I was showing you? If you do a fully pipeline CU execution, and if you don't use subarray level parallelism, what's going to happen is, CU array cannot fetch the data that's preparing the next data. Correct? Very simple. So what we do is we introduce a little bit of logic. We divide those left and right bank subarrays into multiple small subarrays, right? And with some extra logic, right? And then now, while the CU array, the computation unit array, fetches data from one SG, one of these little subarray groups, let's say, okay? The other SGs prepare the next data. So basically it hides even more memory access latency. So that's another one. Okay, so far, any questions? I talk about a lot of parallelism. Any like if you guys didn't understand anything, that's okay to ask questions as well. So okay. Now this is the workload generation part, and this is very important. So this is basically what we call this, again, this hypha group that generates these IBM HE layers, homomorphic encryption layers. So basically any type of a machine learning workload, be it in PyTorch or TensorFlow, it goes to their circ layer. And then, at the end of the day, there's an HE abstraction layer, and then third-party libraries, be it Hion, OpenFHE, or CL, it runs on your CPU and GPU. We do this today. Okay? By the way, if you guys are really interested in this topic, go and check this out. Everything is available, right? It converts AI workloads into an FHA-enabled workloads. Nothing to do with near memory part, just this part. So we look at these workloads. These are really, again, publicly available in some sort of a gateless mode. We did a lot of bootstrapping and multiply chains, ResNets, transformers. These are very large, by the way. Range query, some sorting type of things. Now, for our world, all right, going back to what Onur was saying, if you want to have this near memory, in memory, whatever memory, for it to meaningful, you need SDK. You need software. I'm a hardware designer. I've designed hardware so many years. I sometimes design, I thought, brilliant hardware, but it didn't get adopted because of software. Throwaway work. You throw away all this work because there's no software that can utilize it. Very hard. I mean, it's very important, co-design. I can emphasize this thing. And even for this PIM or any type of these architectures to fly, you need an SDK. You need ease of use. Let me put it that way. Ease of use. All right? I always say people, when I say NVIDIA, is it a hardware company or a software company? NVIDIA is a software company. They invest so much in software. So much in software. It's so easy. Even a person like me, I can create a machine learning model in no time. I don't have to know anything about the underlying hardware. It works. All the stack works. The PIM has to be there. So for that, this PIM to be adapted. So you have an application. For that application, it has to go seamlessly without a developer to worry about it. So a similar mindset. So what we did here is we took the circ layer, then we introduced our optimizations, like a pass layer, you can call it. And this is where, there's a Fendi compiler for this particular work that does clustering, mapping, scheduling, data placement, and then goes to our NDP. So that stack has been built. All right. Otherwise, again, it's no hope. And then these guys collected a lot of results to get the paper in. All right. And so these are the speed ups they posted. Arc is a really state-of-the-art ASIC implementation. So compared to that, they produce about whatever 2.5, 3x speed up, and the other ones are some gigantic numbers. All right. I mean, you can look at it in the paper. It's in the paper. Okay, so this is it. First near DRAM processing, FHE accelerator, and these are the speed up numbers. But again, I think few things to remember. Like I said, remember that parallelism thing that I described. That's basically understanding that how the FHE works and sort of breaking it down to where I can utilize FHE in the best efficient manner. That's, I think, key observation, right? And then after that, how you lay out on a data frame, how you lay out on an NDP with kind of stack die is another contribution, right? And then on top, of course, we run the software and everything. Okay? All good? Everybody's itching to go get coffee. All right, any questions? You have a question? Go ahead.
How about the computation utilization?
Computation what? Utilization? Oh gosh, I think it was very highly utilized, 80, 90. I don't remember. I have to go back and look at the paper. Very high. Especially after that sub-array level parallelism, the utilization numbers like skyrocket. It helped a lot. Right, but right. So my comparison, my statement is really compared to these ASIC implementations and those type of things. Like in FHE in itself, you're right. I mean, FHE in itself is not like another AI type of an application, right? FHE is a very hard problem. Like there will be a lot of times where you cannot fully utilize everything, right? Just because of the sheer of volume of data that you're dealing with. Yeah. Yeah, go ahead.
I have one here. So this number, so for me, well, the important thing, given the initial slowdown, is how it compares with the plain text computation. Do you have the number? So how it compares with the plain text?
Plain text. So this, I think CPU numbers are, let me see. Let me see. I think this, everything is compared to ARC. So CPU implementation is, I think, CPU implementation of the FHE, obviously.
Yeah.
So I will say easily millions of X better. I mean, I wouldn't be surprised, but I have to go back and look at the paper. No, absolutely. It should be a very large number. Go ahead.
Forgive my indolence or perhaps insolence, but you increase basically the computational complexity to make secret computations with the tech.
Yeah,
Well, not the technology, but the method. Yeah,
that's the FHE. Yeah,
exactly.
that's
My
FHE.
question is, how big is the change in the order of magnitude for complexity? Because my question, the point is, AI is already like very
Exactly.
heavy energy consuming.
Correct.
And you want to increase the complexity even more. So
correct.
my real question is like, where does the applicability in practice turn?
No, exactly. So my take on this is, and we discuss this all the time, you know, the first deployment of FHE, if we ever deploy it, I sometimes joke about it, whether FHE is going to be first or quantum is going to be first. So I think, you know, at least I know from some customers there could be some niche applications. I mean, you're not going to run FHE on whatever 70 billion model, right? Otherwise we have to, I mean, already we are consuming whatever nuclear power plant. I mean, we need then 10,000 nuclear power plants, right? Which is impossible, right? So, but there could be some niche application where this FHE can find its ground, right? Where GPU and CPU may not be enough, and you might have to go to a sort of an ASIC-ish implementation. And that ASIC could be just the ASIC itself, or it could be something like we just described here, right? Does that make sense? Think of it niche application, niche domain, yeah. I mean,
and for small models, if you can.
Small models, or I will say relative to small models. Yeah.
If I may continue the second question.
Yeah.
Do you know the EDA industry, like design, automation, and design testing?
So
if you don't know, I'll explain, because this may be possible application. So you have companies that design chips, like IBM, Intel, and stuff.
Yeah, of course.
And what they don't do is they don't design their test solutions. They need to send their design or use third-party software. So one application could be, if you could rephrase the problem of EDA enhancements and do secret computation, then you just put in your design, and it's secret. So you don't have all these layers.
Yeah, that's one example, exactly. That's a perfectly one example that FHE could be helpful if they, especially that application that they are doing is simple enough. Another application is, I mean, there are a lot of applications, health-related stuff, right? Yeah. I mean, you don't want to know the health records, you send it over there, everything is encrypted, you bring it back. And there are other cases where a bank might talk to another bank, they don't want to see their data, they cannot see their data, or they cannot see their model. So they do is FHE sharing, right? So, yeah, go ahead.
To make your implementation specific to HBM?
No. Yeah, I mean, I asked the same question when these guys started working. I said, what about GDDR or you know, it should be fine. It should be fine. That's why I kind of went back to this. I mean, from my, you know, I mean, obviously this is quite far-fetched. You know, I've interacted with memory vendors. I mean, you know, I know how hard it is, but at least it's sort of a directional thing, you know, saying, hey, memory vendors, there might be something out there if you want to build something. And hopefully this might be also useful for some other applications. It's very FHE specific, but maybe there's some other simplifications one can do and then maybe use this for something else. So does that make sense? Okay. Any other question? Yeah, go ahead.
So how many FHE can be implemented in this chips? Also, because RWE is some of the kind of the but I think that there's more FHE candidates in the current. So I'm wondering what kind of the FHE can be implemented in your chip, and what kind of the FHE cannot be implemented here.
Didn't fully follow it, but if you're asking about concurrency kind of a question, is that the question, like saying multiple FHE, different FHE type of operation running on the same substrate? Is that the question? So for example, are you asking, for example, while I'm running some AI model here, can I run something else? Is that the question? Or we can discuss it offline, I mean. Okay, we'll discuss it offline. Any other question?
Burning question. One more.
Yeah, go ahead.
So it's designed for implementing multi-scheme.
Multi-scheme FHE should be able to handle it, I think. Yeah. I mean, I haven't thought through it. That's an interesting question. In theory, it should. Are you working on multi-scheme FHE? Oh, okay. 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 Thank you, guys.
Let's take a 15 minutes break and we will be back at 4:45. If I'm off, let me know.
It's good. Can you check YouTube? Yeah. Okay.
Yes.
Okay. Hello, everyone again. I hope you could find some coffee. So you're going to continue now. I'm going to talk about processing using memory architectures and how you can use them to do processing in memory operations. And then afterwards, Ismail is going to talk about how we can do such operations in real commodity off-the-shelf DRAM chips. So just a reminder what Onur mentioned, process using memory architectures are those that use the analog operating principles of DRAM cells themselves to perform computation. But for this to make any sense, I need you to give you a little bit of background on DRAM organization and operation so that what I'm going to show next related to computation makes sense to you. So if you are not familiar with DRAM, so a DRAM chip is hierarchically organized into several structures. In the bottom level of this hierarchy, we have what's called a DRAM mat, which is a 2D array of DRAM cells. And those cells are horizontally connected to word lines and vertically connected to bit lines. So bit line shares a local sense amplifier and word line shares a local row decoder. So in the next level of the hierarchy, we have a collection of those DRAM mats in what is called a DRAM subarray. And the DRAM subarray shares a global row decoder, and that has a signal that is called global word line that spans across many of the DRAM mats in the DRAM subarray. A global sense amplifier, and the DRAM bank, which is the next level of the hierarchy, not shown over here, has a I/O interface that is used to move data from the local sense amplifier, then to the global, then to the I/O interface, and eventually to the memory channel. So the memory controller issues two main commands to access a DRAM row. The first one is an activate command. Once receiving the activates to a given DRAM row, that DRAM row, the cells in that DRAM row are connected to the local bit line, generating a perturbations in the voltage level of the bit line. And the local sense amplifier senses this perturbation and amplifies that perturbation to a logical 1 or a logical 0, depending on the value that is stored in the DRAM row. Afterwards, the memory controller can read commands to read portions of the data that is stored in the local sense amplifier, a column at the time. And eventually, this column of data is moved to the memory subchannel. So there was a question earlier on that related for Onur about the amount of energy that we are saving when we are doing processing memory operations. And I just want to use this as an example to try to illustrate a little bit better where those big numbers are actually coming from when you talk about processing memory. So this is just one example from HBM2. This is from a PhD thesis from Michael Connor. Now he is at NVIDIA research. And this is the activation energy of when you're doing a column access from the DRAM chip itself. Again, this is from HBM. So we can break down this plot into three main portions. So when you're accessing a row in DRAM, when you access data, you're going to always pay for this activation latency here because you need to read the data and bring the data to the local sense amplifier to amplify that data to a logical 1 or a logical 0. So regardless if you're doing processing memory, processing using memory, or processing near memory, this activation latency is always going to be paid, so independently of the substrate. However, if you are outside the processor, you're going to have large portions of the data of the energy spent on moving data internally inside the DRAM chip. So this is the energy to move data from these sense amplifiers here that I mentioned, this local sense amplifier, down to this global sense amplifier, and eventually to the I/O interface. Oops, I'm moving to the other round. And then you're going to have the energy expense to move data through the I/O channel itself. But note here that this plot might be a bit not very informative if you don't look at the x-axis, which is picojoule per byte. So when you're accessing a cache line, you are repeating this process of internally moving data inside the DRAM chip and externally moving data to the memory channel many bits per data word that you're actually reading. So this accumulates over time. So if you are having a processing near memory solution, for example, since you're moving computation to inside the chip, you're going to eliminate this external energy here per bit multiplied per amount of data that you actually move into that channel. And if you're having a processing near memory solution, some portions of this data movement that happens inside the DRAM chip itself can be eliminated. So, and this is not taking into account also the data that is happening inside the caches, inside the memory controllers until the data gets to the processor. So this is just to give a view of where this large energy saving number comes when you're talking about processing in memory. So basically, you're cutting down this purple part, portions of that purple part, and completely eliminating this red part. This is multiplied by the amount of data that you're actually accessing in your processor. So hopefully this gives a more or less idea where these numbers are coming from. So prior works has shown that we can use these in-DRAM row activation commands to perform computation. So you're going to start very simple. You're going to start by doing row copy operations, and eventually you're going to move to more complex operations as arithmetic operations. So this Onur mentioned this work briefly, RowClone, that shows that we can issue back-to-back activations to DRAM to perform in DRAM row copy operations. So the first activate works as mentioned in the background. It just connects the local the cells to the local sense amplifier, which allows the local sense amplifier to latch the data of the source row. And then the second activation connects the destination cells to the local sense amplifier. And since we have the previous latch the data from the source row in the sense amplifier, and the drive of the circuitry in the sense amplifier is stronger than the capacitance in this local bit line here, we are going to end up storing the data that was previously latched to the destinational cells, hence perform these in-DRAM row copy operations. RowClone shows that by doing DRAM row copy operation like this, we can significantly reduce the latency of copying a 4 kilobyte row and also the energy. Because if you go back to that diagram that I just mentioned before with the energy, we are completely eliminating any data movement from the local global sense amplifier and also to the interface. I'm just paying the energy of the activate in this operation. So this is just another view of how the same thing works. So I connect the source row, this is the DRAM cell, to the local sense amplifier, which amplifies the difference in the voltage level and store the amplified difference. And then I connect the destination row to the local sense amplifier, and then the data that was previously latched is copied to the destination row. So you can exploit this way that it works here is mostly for rows that are in the same DRAM subarray, but you can also pipeline these operations via the shared internal bus in a DRAM chip to move data from one DRAM row to other DRAM row in different DRAM subarrays. And you can also do the same to move data across different DRAM subarrays in the same DRAM bank. We are going to improve this a little bit later on. So all of these are at very low area cost, because basically I don't need to add anything to the peripherals to do these consecutive DRAM row activations. So this is very nice. We can do in DRAM row copy. But what about something more interesting? What about Boolean operations and or not operations? So we can do those operations in DRAM by following a similar approach, but instead of doing consecutive row activations, now we are going to do triple row activations. We are going to activate 3 DRAM rows at the same time. So when you activate 3 DRAM rows at the same time, the 3 DRAM cells simultaneously perturbate the local bit line. And since the circuitry here in the local bit line is a differential sense amplifier, this differential sense amplifier is going to pull the voltage level to the majority of the voltage level stores in the 3 DRAM cells. So in this example here, the majority of blue, yellow, and blue being all blue. And similarly, this approach significantly reduces the operation, the energy of doing majority of 3 operations compared to moving the data out of the DRAM chip itself. This is again another view of the same thing. Here we have 3 DRAM cells, A, B, and C. The A and B stores 1, and C stores 0. When you activate them 3 at the same time, they generate a perturbation to the local bit line. This amplifier is enabled, and this perturbation is amplified to the majority of 3 of the voltage level stored in the DRAM chip themselves. So basically, the final state of the computation is going to be, if I can control one of the rows, it's going to be either A or B, or A and B. But basically, what I'm doing is a majority of 3 operations inside the DRAM chip itself. So now we have row copy, and we have majority of 3 operations. Can I make this functionally complete compute energy already, or am I missing anything to make this, for example, addition out of this? Any guess? We did a NOT operation. So the nice thing is that DRAM, by definition, already have a NOT implemented inside this chip. So basically, that box that was the sense amplifier that I was not showing earlier is this circuitry here. It's 2 back-to-back inverters connected and constitutes the sense amplifier. So we can implement NOT operation by basically rerouting one of the outputs of one of those inverters back to the DRAM cell. So using those dual contact cells. And then we can have majority of 3 and NOT, which is a function complete set of operations. You might ask, and many people have asked, especially memory manufacturers, the fact that this rerouting of the signal here back to the DRAM cell to be very costly because of the limited number of metal layers that you have in the DRAM chip itself. And this is true, but this is not the only way of implementing NOT. So other works have proposed different ways of having this NOT realization inside the DRAM chip. Sorry. One easy way of doing so is every time that I store A, I also store A bar inside the DRAM chip. That would be trivial, but also would consume half of my DRAM chip in terms of capacity. Another way is redesign the sense amplifier. Instead of having this folded architecture where one sense amplifier is shared across neighboring DRAM subarrays, I can have a single sense amplifier connecting a single DRAM connected to 2 DRAM cells. One DRAM cell stores the regular data, and the other DRAM cell stores the bar version, so then the negated version of the particular data. Again, this design would lead to halving your DRAM capacity compared to the folded architecture. But at the same time, you don't need to reroute that signal back to the DRAM cell itself. Another way is to using different designs for the sense amplifier. This is a bit more cumbersome the way that it works, but I'm just having it here to highlight that there is not only a single way to achieve the NOT operation. There are different designs that leads to different trade-offs depending on what you want to pay. So now we have majority of 3, we have copy, we have NOT, and now we have everything that we need to implement more complex arithmetic operations inside the DRAM chip, right? And this is what we did in this work called MIMDRAM. What we do basically, let's say that you want to implement a adder inside the DRAM chip, and then you have a simple 1-bit RIP carry adder. The first thing that you need to do is that what I'm doing in the DRAM chip is basically majority and NOT operations, right? So I need to convert this RIP carry adder circuit that have AND or NOT operations into optimized majority NOT representation of the same circuit. And gladly, there are ADA tools that allow you to do this conversion efficiently, and we can use them to do so. So after we have this majority gate here, majority NOT representation of this RIP carry adder that to do the addition, what I need to do is map each one of those majority graphs, majority nodes here, into triple row activations, into basically issuing those triple row activations to the DRAM chip. So we go through this triple row activation one by one. So let's say that I want to add 2 arrays, array A and array B. Each array has as many data as columns inside the DRAM chip, so around 65,000 elements inside the array. And each element of the array is only 1 bit. So basically what I want to do is add blue plus blue, here is 1, 1 plus 1, and I want to have 2 as a result. inside the DRAM chip itself. So I go to the majority graph here, which tells me how to do this operation inside the DRAM chip. So first I need to activate row A, row B, and row carry in, which stores zeros at the same time. This is going to generate the carry out row here, which is going to be 1. Then I don't have it here in the slide, but then I move to the next majority node, which is going to activate A bar, B, and carry in. This is going to be 0. And finally, I move to the final majority node, which is going to be A and the output of the previous 2 majority gates, which is going to be 0. So in the end, in row carry out, I'm going to have a row full of 1s. And in row sum, I'm going to have a row full of 0s. And if I read this data vertically, this is going to be 1, 0, which is 2, which is the output of my addition operation. Note that we did this for 1 bit. What if I have 2 bits or 3 bits or 32-bit integers? So this process needs to repeat for the amount of bits that you have in your data word, 1 bit at a time. This is all to say that if you do computation like this in DRAM, our DRAM chip now becomes a very wide bit 0 engine. Very wide, meaning that I have as many SIMD lanes as I have DRAM columns in my DRAM subarray. And SIMD, because I'm doing the same operation, the same majority of 3 operation across all of the DRAM columns inside over multiple data stored in those DRAM cells. So note here that those majority gates here are not necessarily implemented inside the DRAM chip. I don't have a majority gate or a logic inside the DRAM chip that is implementing this majority gate. I only have triple row activations and in DRAM row activations that when I do them, the effect of this activation is a majority of 3 cell. So this is just a representation. Is there any question on how this works, or it still looks like magic?
You have to have some third row that you preset to perform that operation. So in this case, it's TE. So how do you perform those control logic and set operation on that row? So you need some kind of a controller or some kind of an arbitrator to set those nodes, right? So now, how does that happen, or like where the control signals are, how that row is activated, how can you elaborate on that?
Yes, yes. So all of this is an oversimplification of this mechanism. So the way that it actually works is that inside the DRAM chip, we have pre-initialized rows with all zeros or all ones. It's only 2 of them. We don't need many because once you have one row with all zeros, 1 rows with all ones, we can do the row copy operations to replicate that as many times as we need it. But we have one designed row for that, and that is by design over there in the DRAM chip. And then we have a controller in the memory controller that is responsible to, we call this sequence, the sequence of operations here, a microprogram. And the controller is a modification of the DRAM memory controller. It's responsible to generating the activation and precharge and row copies operations as this microprogram dictates. And this defines the controls and which row needs to be copied at each given moment in time. But all of this can be predetermined once you have this majority not graph optimized from the initial and or not graph, basically. So I went backward. So basically, you do this step first. You convert whatever you want in majority not. Then you generate this microprogram, store in the memory controller, and the memory controller dispatch those instructions according to realize, for example, addition. And this is how it works. Another question? No. Okay, so all of this is very nice. Ismail is going to briefly talk about how we can do those operations in commodity off-the-shelf DRAM chips. I'm not going to spoil this. Even though this is fun, enabling these in real chips is still quite complicated for a myriad of reasons. I'm going in this talk here, because of time, I'm going to talk about two of the problems that this substrate might have and how we can solve them. You start with how we can map applications down to the substrate and how we can efficiently implement those operations over there. So as I mentioned earlier, if you do computation like this in the DRAM chip, my DRAM chip becomes a very wide SIMD processing substrate, right? And my SIMD width is 65,000 columns at the same time, or 65,000 elements. So how often do you write a code that iterates in a loop that always performs 65,000 operands at once? That we went after this question in real applications, and we realized that, surprise, surprise, not often. And if you don't use if you don't perform these computations in that granularity, doing process using DRAM operations, you're going to have severe throughput and energy waste of your substrate, because you're going to be operating at portions of the DRAM row at a time. And activation, even though, as I mentioned at the beginning, right, in that plot, activation is not might not be the most expensive operation when you're reading data from the outside, but it accumulates over time, and you always need to pay for that. So you're going to end up wasting energy in those activations over unused data. The second part is that when I did the addition example, I mentioned that I have two arrays, and then I have doing A plus B, and I was generating a third array, right, C, sum and carry out. However, if I want to add a single array into a scalar in a reduction operation, there is no way for me to do that, because there is no communication path across the DRAM columns inside the DRAM subarray. So it's the interconnective problem that Onur mentioned earlier. The third problem is that computing, mapping codes down to the substrate is very complicated, because I'm talking about these activations that you need to do one by one in order to realize the operation. But you as the user just want to use an add operation and then get the output of that add operation, right? So I don't want the user to have to think about DRAM activates to realize the operation. So basically, the problem that we are trying to solve here is that there is this large and rigid excess granularity of the DRAM chip that limits the applicability of those in-DRAM operations to real-world applications. And we want to solve this problem. So the way to solve this problem is actually an old idea. It's called fine-grained DRAM activation. So in the DRAM chip, when you are accessing a DRAM row, even if you are not going to access the entire DRAM row in the follow-up read access, the entire DRAM row is activated and brought to the local sense amplifier, wasting energy if you're not going to access the entire DRAM row in the follow-up DRAM columns. So this problem happens because this global word line that I mentioned earlier is spans across all of the DRAM mats inside the DRAM subarray. So prior works has proposed this idea of fine-grained DRAM row activation, which basically segments the global word line, allowing one to access individual DRAM mats doing a DRAM row activation. This improves energy efficiency for many applications. For example, graph processing applications that have random access. So this is nothing related to PIM, but at some degree is used in commodity DRAM chips, transparently from the program, from the user. We are going to use this idea to do processing in memory, or process using memory in three different ways. First, we are going to improve SIMD utilization by only issuing triple row activations to the portions of the DRAM row, so the DRAM mats, that has the target data. For the other portions of the DRAM mats are not going to activate. This allows us to do something else. We also allow us to do multiple instruction, multiple data execution, because for data-independent process using DRAM operations, now they can be executed at the same time across different DRAM mats inside a single DRAM subarray. Here, it's hard to see the degree of parallelism that you're actually achieving when you're doing this, because I'm only showing 4 DRAM mats, but actually inside the DRAM subarray, we have around 128 of those DRAM mats. So you can ideally have 128 different operations executing at the same time inside a single DRAM subarray, as long as all of those operations are independent of each other. So it's a very high degree of parallelism. Second, we can enable interconnect communication across the different DRAM METs by doing some simple modifications to the peripheral of a DRAM subarray to move data from one DRAM MET to another. And basically, it enables us to do in-DRAM reduction operations. And third, a nice property of those DRAM METs is that we have as many DRAM columns in a DRAM MET as SIMD lanes in modern SIMD ISA instructions. So have 512 DRAM columns inside the DRAM MET. And if you think about AVX 512 instructions, they also have 512 vector lanes. So basically, we can map those AVX instructions down to processing using DRAM operations transparent from the user. Based on these ideas, we propose MIMDRAM, which is a hardware software co-design process using DRAM system for efficient and easy to program process using DRAM operations. So I'm going to briefly illustrate how this works. So in the hardware side, we do some modifications to the DRAM subarray to enable us to individually access portions of a DRAM subarray, so those DRAM METs. We also implement some intermet interconnect that allow us to move the columns of data from one DRAM subarray to another one. And also a controller, the memory controller, that allow us to schedule independent computations to different DRAM METs. So those are those 128 METs that I mentioned, and control them individually, doing process using DRAM operation. On the software side, we implement 3 LLVM compiler passes that are responsible for code identification. So basically what we do here is that we take the LLVM auto-vectorization loop that already exists in LLVM, and we modify this auto-vectorization engine to generate vector instructions to very wide SIMD register sizes, because we have those very wide SIMD registers inside the DRAM subarray. Then in the second pass, we add some metadata to the generated vector instructions in order to identify which instructions can be executed independent of each other, which is inside the same DRAM MET, and which instructions needs to be executed can be executed concurrently because they have no data dependence across different DRAM METs. And the third pass basically generates the binary for the application. So in the paper, we have several other system integration challenges that we solve in this work, but I invite you to check out the paper for that. So the simulation infrastructure is available online, and we use 12 workloads for 4 benchmark suites to evaluate this mechanism. And then we see that compared to using a coarse-grained activation, we can significantly improve energy efficiency for those 12 workloads. And why is that? Because now we are not suffering from underutilization anymore. And not only this, we are exploiting those 128 DRAM METs in a DRAM subarray at the same time for computation. So this enables us to bridge this gap of performance compared to a substrate that would use this coarse-grained DRAM activation for processing using DRAM computation. So basically, you're adding yet another excess of parallelism on top of the substrate. Compared to other processing in memory solutions, we see also performance improvement because, again, we are not adding much logic to do the computation. So is there any question related to MIMDRAM? Question there.
Maybe not necessarily MIMDRAM, but just the whole, just going back to the basic arithmetic operation of doing an add, for example. What is the rate of error when you're doing kind of this processing within memory? And is that kind of, like, for example, the rates of bit flips or something, is that kind of comparable to processing in like traditional?
So Ismail is going to talk more about that. In these works here, we are doing all of this in simulation, so we're not accounting for generated errors from commodities off-the-shelf DRAM chips. And there is a reason because of that. So DRAM is not designed to do this. And when Ismail is going to give his talk, you're going to see that there is an error when you're trying to do these operations in real DRAM chips right now today. And this error mostly exists because the sense amplifier is not strong enough to sense multiple rows. But there is a solution to that. It's just to make the sense amplifier stronger. So if by design if the memory manufacturers has this type of operation in mind by design, we can make these operations mostly reliable by redesigning this local simplifier to be strong enough to sense 3 DRAM rows. Of course, this comes with costs. We will need a larger simplifier, but maybe this is a product line by itself, right? Because now your memory is not just memory, it's also compute. So over here, we are not accounting for that composing error that one operation is going to generate on top of the other. Another question there.
128 computations on different independent maths in parallel, and from what I gather, like each operation may require like multiple activations of rows and like it's a complex operation. So how do you issue so many DDR commands?
At the same time, right?
Yeah.
So we cannot issue all of them at the same time because you need to respect default, which is a time parameter that defines that you can do is a time window that you can do 4 activations per bank group. But this activation basically takes time, right? So and it's faster than the bus. So you can activate X amount of banks, wait for TFO, and then activate. You can pipeline basically across.
Are you limited in some cases by like the number of comments you can issue? Or?
So it depends on there is this problem with TFO. If you relax TFO, and some memory manufacturers do so for real processing memory solutions. So if you relax TFO, then you're going to be bottlenecked by the channel itself, the width of the bus, because it's not enough to issue the activates for all of the 128 at the same time. So we did a calculation for this work. So if you are thinking about DDR4 chips, the bus becomes the channel becomes a bottleneck, and you can activate, if I'm not mistaken, 68 of the 128 met at the same time. Don't quote me at this number. Basically, it depends on the frequency of the bus and the frequency and the number of pins that you have. If you have DDR5, because the bus is faster and you don't become bottleneck. You can activate all of them, assuming that you can relax TFO. And then we have that as a footnote in the follow-up paper that I'm going to mention next. Okay. So great. Is there another question?
So the programming model seems a bit strange to me because maybe the compiler would issue explicit computation like processing in DRAM commands, but sometimes the data is already going to be present in the caches, or in the instance of AVX, it might already be in the right registers. And in that instance, you would actually not want to bypass the caches to the registers and go to. So my question is, is there some good way to have a good programming model that actually makes sense?
So the programming model does not make sense because I didn't explain the programming model very well. So because it's very complex actually. So the way so for all of these that I mentioned to work, there is a trick that was in the background slides that I don't know if anyone catch, but the data needs to be transposed. So you need to store. So if you have a 8-bit integer, usually in DRAM, those 8-bit integer is going to be stored inside the single DRAM row, spanning different DRAM columns. And this is how the system, the caches are expecting the data to be organized. However, if you want to do addition, you need to propagate carry across different bits. And then again, there is no connections across columns. So what we do, we transpose the data. So instead of storing the data horizontally, we are going to store the data vertically. So every single, I'm going to move a lot of slides just because I want an example of something. Okay, so here is a better example. So all of the bits, so here I have A and B. Each one of them are 2 bits. So I store the elements vertically inside a single DRAM column. So when I do addition, the carry is going to generate and it is already going to be there in the column itself. This means that someone needs to transpose this data. So I don't want to store the data in this transposed format in the DRAM chip across, even if you don't do processing memory computation, because there are reasons why the system expects the data to be horizontally. So there is basically now I have this heterogeneity in data format. Because of that, there is a transposition engine that's usually placed in the memory controller that usually when the data, you need to think that all of you're operating over this huge amount of data, right? So it does not fit in the caches. So eventually when the data is evicted to the memory chip, this transposition engine is triggered and transpose the data to this vertical data format over here. So basically, this means that when I trigger the process using DRAM computation, hopefully my data is not going to be in the cache anymore because it was evicted and transposed. And if there is still some pieces of data that are in the caches, CL flush instructions need to be issued. And the data is then evicted and transposed and stored into the DRAM chip itself. And then afterwards, the computation can be triggered. And the compiler itself does not necessarily trigger activations. The compiler does not know anything about DRAM. And there are reasons why we want to make the compiler transparent to hardware specifications. I'm not going to get into those reasons, but what means that the compiler only issues what we call BBOP instructions. Maybe it's here somewhere. Here. So so the compiler just issue, for example, adds of A and B that store C, and in this met here is just a metadata. It does not mean a physical met. It's just like in meta label A, and this is going to be translated later on as page faults and address translation happens. And then the controller that I mentioned that was implemented, the memory controller, then translates that BBOP add into activate stores, because this is our add in memory controller. So there is a lot of levels of indirection happening in the system so that this can work, because we need to touch a lot of different things. The memory controller becomes a front end of a processor, and it started very simple, and as the system, as we discover that DRAM can do more things, the memory controller becomes more and more complex. There is no reason for this to be the memory controller inside the SoC of the processor. This is just one design choice. If you have a 3D stack chip, for example, where the portions of the files are implemented in the base die of the 3D stack chip, this can also be moved there. But basically, whoever controls DRAM now also needs to control computation. Yeah. Hopefully that was more or less intuitive. Okay. Yeah, this is why I mentioned this list here. Just make the paper very dense because it needs to touch a lot of integration stuff. Okay, so hopefully that explains more or less the programming model, and this is great because then the second problem that I'm going to try to illustrate becomes easier. So as I mentioned, this substrate became multiple instruction, multiple data, SIMD, bit serial execution model, right? So a lot of keywords here, but this is still going to have inefficiencies when you're doing those computations. So the first inefficient is that usually you as a C programmer have encountered that many times probably, if my computer is not charging, sorry. If it dies, it's problematic. Sorry about that. So you have encountered the fact that you are storing elements that are relatively small in data formats that are very large. Or this might happen because, for example, in C, you don't have anything large smaller than a chart, which is 8 bytes, right? 8 bits. So if you have an element A that stores 4, for example, the 3 most significant bits is going to be the data that you have, but the 5 most significant bits is going to be full of zeros. When you're trying to do the addition, for example, from elements that have this property, which you call narrow values, you're going to end up computing on inconsequential bits. Basically, those bits does not contribute to the output dynamic range of the operation. So this is not other than storage, this is not a problem for your processor, because when we have a ALU that does bit parallel addition, the ALU is operating all of the bits in parallel. So I don't care if I'm operating in a bit 0 here or a bit 1 here. But since this substrate becomes bit serial, I'm operating each bit individually. When I start operating after bit 2, operating bit 3, 4, 5, and 6, all of those bits are going to contribute to the latency and the energy of my computation, which is going to be wasted on all of those inconsequential bits. So you might ask how often those sequential bits happen. So how often those narrow values happens in real applications, and we quantified them in this plot here. So in the x-axis have 12 different applications and then you're going to show some distribution plots that shows the bit precisions. And the main takeaway here is that in all of those applications, we see those narrow values happening. So here we have 32-bit integers, and as you can see, we can reduce the bit precision for those 32-bit integers for loops in these applications on average from 32 bits to 20 bits, meaning that we can use these narrow values to stop the computation when you're doing those triple row activations in DRAM, hence saving energy and also saving in latency. You're going to ask how we can then identify those values because my arrays are generated dynamically, right? I'm going to show how this is done later on. But just keep in mind that if there is a way for us to dynamically identify which bits are consequential and which bits are not consequential, I can just compute on the consequential ones and skip the inconsequential ones doing process using DRAM operation. So the second problem that this execution model has is that those operations can become inherently slow because I need to move data from bits that is computed from one bit from data that is computed to another bit. So think about carry adder generation, right? So I'm doing the addition. I do the activations for the first 3 majority gates here. Then I need to move the carry out bit generated from bit 0 to bit 1, and then I can start doing the addition from the other bits, right? So this creates a serialization. This carry propagation creates a serialization of the computation that happens across bit 0 and bit 1 for that RIP carry adder example that we mentioned before. However, if you look at this circuit here, you can see that once I solve that interbit dependence from the carry generated from bit 0 to bit 1, I have many majority gates that actually does not depend anymore of that carry that was generated. So basically, if there is a way for me to fastly compute that carry out data and distribute those bits across different DRAM subarrays, I can compute those individual majority gates across different bits at the same time, hence reducing the latency of the operation. So we are going to do this by using this specialized data mapping called 1 bit per subarray, where we are going to take different bits of a data word, and you're going to scatter those bits across different DRAM subarrays inside the DRAM bank. And also, you're going to implement some inter-subarray interconnect that allow us to move data from one DRAM row to another DRAM row using those in-DRAM row copy operations. So how does this help? So basically, we compute the carry for bit 0 here in subarray 1. And after that is done, we move the generated carry to the neighboring subarray that has the bit 1s for the computation. And now, since the carry was resolved, I can at the same time compute the remaining majority gates across bit 0s and bit 1s in those 2 DRAM subarrays at the same time, hence in saving cycle for the bit 0 operation. So, okay, we can reduce the latency using those narrow values that I mentioned earlier. We can further reduce the latency by using this interbit dependence across this scatter data layout. But still, if my precision of my computation is very high, if I have high precision operations, still there is no way. I'm going to have to pay for the latency of the bit 0 operation because latency is going to scale either linearly, depend if it's an addition or a subtraction operation, or quadratically for multiplication or division operation. So how do you solve this issue then? Our solution is to use other data representation formats, especially there is this format called redundant binary representation, RBR, which each bit position is represented by 2 bits. For example, if I want to store 3, I can use 4 bit positions, 0, 1, 0, and -1. And this redundancy that is built in the data representation allow us to implement arithmetic without extensive carry propagation change. So when you're doing a RBL-based adder, the carry propagation is going to be limited by at most 2 positions. So this means that the latency of the operation is going to be mostly independent of the precision. So we can use this redundant binary representation, this alternative data format, when you need to do high precision processing using the DRAM operation. We don't want always to go here because sometimes, depending on the precision, the latency might be lower doing bit 0 operations. So you need to adapt as well, depending on the bit precision, which data format you're going to use. So based on all of this, we propose Proteus, which is a framework that dynamically and transparently adapts the representation of the process using DRAM operation, the bit precision, and the data formats for the target operation. So Proteus is implemented as a harder substrate in the memory controller. Again, we are overcomplicating the memory controller because now we also need to first identify what are the data that is stored in my arrays. However, I don't need to store the entire data array. I just need to identify the largest elements in a data array and store that information. Because then I can compute the upper limit of my bit precision. And then when I do the triple row activation, the operation itself, based on this upper limit, I can set the target bit precision for all of the elements inside the array and select which is the most performant implementation of my in-DRAM operation for the target operation. So I didn't go into details here over time, but this is leveraging the fact that, as I mentioned earlier, since the data already needs to be transposed anyway prior to the computation, when you're doing the transposition, we are also trying to figure out which are the largest elements inside that array. And based on that, setting the target bit precision for the bit 0 operation. Question?
How do you define object?
What is the object itself? So, as I mentioned earlier, there is a compiler pass that identify vector instructions, right? So you can backtrack. So those are the addresses that vector instructions are going to consume. And then there is some specialized instructions that we mark in the memory in the binary to mark like, oh, address A was vectorized. The input of a vector instruction was a vector A, which is going to be used for process using DRAM computation.
Work together with the memory control teach this data, right?
So the compiler just needs to trigger the instruction. So not more than that. So the only thing that the compiler needs to tell is to the memory controller there is this address range here. Watch out for this memory address. It's the only thing.
Basically reinterpret it using the same object, but once like it's 4-bit or 8-bit, like do you just bail out of circumstances and like do not optimize it on the compiler level, or do you have any tricks to handle touch?
So we don't optimize the data format in the compiler level. So what we do is like we also want to keep system compatibility. My English stopped. Compatible with the other parts of the system, right? So it's very hard for the compiler to actually predict what's going to happen later on, and this is a dynamic process. So it's very hard to also pre-statically define, oh, my precision is going to be 17 bits for array A, for example. So what we do basically is just when you are doing triple row activations in the DRAM chip, it stop at bit 17. But the data on the allocation is still 32 bits or whatever the compiler or the programmer decided by itself. So when the data is actually read back, the entire 32 bits is read. But when you're issuing the computation, only the appropriate number of bits are actually considered.
Appears before each computation.
Appear before each computation happens, yes. Yeah. So hopefully it's more or less clear. Okay, so yeah, in the paper we have many more analyses, including the data format conversion procedure and overheads. And again, we evaluate this using those 12 workloads, and you see significant improvement compared to coarse-grained-based process using DRAM, especially because if you look at the gap here, the majority of the benefits comes actually from using those narrow values when you're doing bit zero operation. So by early termination, the computation, we can significantly improve the performance. And if you look, the energy consumption is going to be quite similar as well, compared to using static data representation for the process using DRAM operation. So they have many more results in the paper, but during the interest of time, I'm going to give the stage to Ismail. Is there any burning question? So as a summary, we start very easily. We start doing in DRAM row copy. Then we move to Boolean operations in DRAM, majority of 3 and not. And then after that, we start complicating the system. We're doing SIMD arithmetic operations, then MIMD arithmetic operations, and then data-aware SIMD or MIMD arithmetic operations inside the DRAM chip itself. And then this is basically the summary of what we saw. And now you're going to see how we can do that in real commodity off-the-shelf DRAM chips. Is there any question?
Yeah. How custom you need to have like the DIM module, because I think the memory controllers were already pretty advanced, so they could be programmed with instructions mainly for testing purposes, but you could implement testing algorithms. So probably all the DRAM instructions you can implement that is in existing architecture, but to have the negation, you had to modify the
DRAM
physical array.
Yes, yes.
So did you manage to do that and had a physical chip?
So we don't prototype chips in Safari, so we don't, actually, I don't think anyone, well, I'm not going to overclaim, but like manufacturing DRAM is a very costly process that only few entities in the globe can do. So we don't tape out DRAM chips. We do some SPI simulations to try to estimate the latency and area overhead of our modifications. And according to our simulations, that rerouting of that NOT gate incurs non-trivial area to the DRAM. It still is areas like it's less than 1% area overhead, but it's still area overhead. This number has been disputed by other research papers. There are papers that says that if you actually take into account the space in the meta layers, actually becomes much more complicated.
That's another overhead on the physical array that's super expensive because you
Yes.
do 1% of the controller.
Yeah, it's in the array, which is very expensive. Yeah.
All okay, yeah? Didn't need custom memory controller.
We did RTL synthesis of the controller itself, because then we can still figure out the area. I don't remember the number off the top of my head, but it's very mild actually.
Second question, because to do that, I understand the memory controllers nowadays, I believe they very often perform scrambling for the energy dissipation reasons. And you cannot do that in here because you rely on
the data layout.
Yeah, physical array. So do you anticipate any problems with that? Because you will be hammering very nearby cells very hardly.
I'm going to let Ismail answer the question, because he's going to talk exactly about that. Yes. Okay, any other burning question for me?
What's the boring question?
A burning question, sorry. Any burning question? If you have a boring question, also feel free to ask. So if not, thank you very much. I'm going to give the stage to Ismail.
That's Ismail going to go. Really. I changed the
These slides?
Yes.
I said that
From
Ismail is
the-
going to do a lot of things. Oh, of course,
Yes.
you're fine.
I need to do speedrun.
You need to speedrun.
Yeah, 3 papers on my computer.
Is each one?
PX, yes. Because the other ones only contains pattern. Okay. Maybe I should stand here. How many minutes? How many? Tell me. 30?
Very good.
Okay. Should I start?
Yes.
Hello, everyone. I'm Ismail. I'm a PhD student at Safari in ETH Zurich. I'm gonna speedrun 3 papers. 2 of them were published last year. One of them was HBCA and one of them was DSN. And I'm gonna foreshadow our new upcoming ISCA paper about row hammering with processing using DRAM. So the first one is functionally complete Boolean logic in real DRAM chips. So the motivation is processing using DRAM can be used for data. Yes. Ah, okay. Okay. So yeah, POD can alleviate data amount bottlenecks, and prior work show that existing DRAM chips can do like majority and 2-input and then OR operation. But proof of concept demonstrations on prior works before this work couldn't do functionally complete operations, not operation, or more than 2-input and then OR operation. In this study, we tested a total of 256 DDR4 chips from 2 major manufacturers, and we observed that off-the-shelf DRAM chips are quite capable. They can perform NOT and 2, 4, 8, and 16 input AND, NAND, OR, and NOR operations with relatively high reliability. And data pattern and temperature only slightly affect the reliability of these operations. Since we have a lot of backgrounds, I'm going to skip these parts. So this is like data movement bottleneck that we have. And this is processing memory. Hopefully you know that. And this is DRAM chip that we have. Again, Geraldo gave a very nice background on these things. And the one important thing to emphasize again is that the physically adjacent subarrays share sense amplifier, which contains back-to-back NOT gate over there. So we're going to leverage this component to realize such operations. So we also know that activate column accesses and precharge. So our goal in this paper to show the capability of off-the-shelf DRAM chips beyond just storing data and characterize this reliability. And we demonstrate that they can simultaneously activate up to 48 DRAM rows in 2 neighboring subarrays. They can perform NOT operations with up to 32 outputs, and they can up to perform 16 input AND, NAND, OR, and NOR operations. So to be able to test real DRAM chips, we use a open source DDR4 testing infrastructure called DRAM Bender. This allows us to have a fine-grained control over DRAM commands, timings, and temperature. We test a total of 256 DDR4 chips from 2 major manufacturers, and we cover different die regions and chip densities. You can think of that different DRAM architectures. And for that one, assume that we have 2 subarrays here. For our testing methodologies, we have 2 neighboring subarrays. They share a sense amplifier. And assume that they have 2 rows here, row A from subarray X, row B, and subarray Y. What we do is that we issue activate, precharge, and activate commands to these things. And we sweep row addresses over there, and the timing parameters between activate to precharge and precharge to activate. So let's see how we activate multiple rows. So the key idea is to activating two rows in quick succession, and those can simultaneously activate multiple rows in neighboring subarrays. So here, recall this pictorial example here. If we just obey the timing parameters, which is shown here, we will activate only a single row at a time. However, if we greatly violate, like too greatly violate these timings, we observe that we can activate many more rows, up to 32 rows in one subarray and up to 48 rows in 2 neighboring subarrays. So in order to understand which rows and how many rows we activate, we sweep these row addresses and they show us like some of them activate 2, some of them activate 4, like up to 32. It depends on actually the row decoder design that we have in real DRAM chips. So they, as a maybe insight for that one is that we have a hierarchical row decoder circuitry to like very quickly decode the row addresses. So because of that, if we greatly violate these timings, so we will activate a lot more intermediate signals, and they're actually connected to the other rows that are not activated in this command sequence. As a result of that, we activate many more rows in multiple subarrays. So for the key results, we observe that there are 2 distinct sets of activation patterns when we activate multiple rows. One of them is exactly the same number of rows that are activated in each subarray. We observe that we can activate up to 16 rows in each subarray, a total of 32 rows. Or twice as many rows in one subarray are activated compared to its neighbor. And we observe that we can activate up to 16 rows in one subarray while activating 30 rows in its neighbor, a total of 48 rows. And there are a lot of hypotheses and results in the paper. So let me quickly go through the NOT operation. So we see we can activate multiple DRAM rows in neighboring subarrays, and let's see how we leverage this. So recall that we have NOT gate in between 2 neighboring subarrays. And the key idea is to connect rows in neighboring subarrays through a NOT gate by simultaneously activating them. Basically, if we activate source, it will drive its value to its bit line, and it will have the negated value in the other side of its terminal. And if we activate destination without deactivating anything, we will have the negated value of the source in the destination. Let's see this NOT operation at lower abstraction level. So recall we have source and destination, and our DRAM is precharged. Bit lines have VDD over 2, and source and destination initially have ground. So we issue an activate command to source, which will connect the source to bit line, and we wait for nominal timing parameters, and it will drive the bit line to ground, which since source has the ground, and the bit line bar, which is the destination's bit line, will have the VDD. So if we violate the timing at issue, precharge and activate back to back, we will connect destination to bit line since we issue an activate command. Since we violate the timing, we didn't give a time to DRAM to precharge. So as a result of that, sense amplifier is still enabled, and destination's bit line is still VDD. And as a result of this, if you wait long enough, again, the negated value of the source is written to destination. So we characterize this by sweeping the row addresses again and the DRAM chip temperature. And to assess the reliability of such operations, we introduce a metric called success rate. Success rate for a DRAM cell refers to percentage of trials where the correct output of a test operation is stored in the cell. So assume we do a total of 10,000 trials. For example, for this example, assume we have 4 trials and half of them are failed. Success rate for this specific cell is 50%. So we have 2 main key takeaways from this experiment is that off-the-shelf DRAM chips can perform this NOT operation with up to 32 destination rows, and temperature has a small effect on the reliability of such operations. And here is the first result. And x-axis, we have the number of destination rows, and the y-axis, we have the success rate distribution. As you can see here, there's at least one DRAM cell that can perform the NOT operation with 100% success rate. It's actually a lot more than one DRAM cell. And we conclude that off-the-shelf DRAM chips can perform this NOT operation with up to 32 destination rows. And let's see the impact of temperature. So we use destination cells that can perform the NOT operation with more than 90% of success rate. And we observe that from 50 to 95 degrees Celsius, there is less than 1% variation in average success rate. As a result of that, we conclude temperature has a small effect on the reliability of NOT operations. That was not. Do we have any questions about NOT? I can get that. Okay. Yeah.
Do you expect these results to vary in between manufacturers and DRAM chips, or do you think they are generalizable?
So we test 2 manufacturers, and we see that they're pretty similar, especially for NOT operation.
And maybe a follow-up question would be,
Mhm.
do you expect with new processes,
Mhm.
new technologies, for these parameters to like change?
We test those one as well in the papers. I don't remember it right now, but they're a bit irrelevant. Like some older ones have very good, let's say, reliability, and some newest ones as well. But in between, there are some bad ones. So it's really, there's no correlation right now. Maybe we need to test many more DRAM chips, more than 250. A good question. Thanks. Yeah.
Up to 32 rows.
Yes.
Can you, but you cannot choose which ones, right? Like it depends on the
Yeah, it depends on the row decoder circuitry, definitely. Yeah. To be able to understand those things, we need to do like a lot of reverse engineering.
But once you reverse engineer a specific model,
Mhm.
then this is repeatable, right?
Yeah, it's the same. Even like for the same chip density and the die revision, basically the same DRAM architecture, all of them are the same. We test that, like at least 10 of them, for example, the same architecture had the same row decoder circuitry. Yeah. Good question. Again, so let's see how we leverage NOT and this multiple row activation to perform and then OR operation and then NOR. So Onur actually explained it really good, but let me give you the key idea again. So we try to manipulate the bit line voltage to express a wide variety of functions using multiple row activation. Here recall we have two neighboring subarrays. The top one contains A and B, and the bottom one contains X and Y, and this is per charge to reference voltage. So if you activate multiple rows at the same time, what happens is that these bit lines will have the average voltage of the cells that are simultaneously activated. For top subarray, it will become the average of A and B. For the bottom subarray, it will become the average of X and Y. And as after the charge sharing, sense amplifier will compare which one is higher, and depend on that, it will drive the bit line to 1, and for the other one, it will drive to 0. So let's see how we do that in real DRAM chips. So here we have two subarrays, reference subarray and compute subarray. Reference subarray has VDD and VDD over 2. We can actually store VDD over 2 in real DRAM chips using a prior work technique called FRAC DRAM. And in the compute subarray, we have X and Y. So assume we issue activate per charge activate, and this command sequence activates these 4 rows simultaneously. So, and recall that when we activate these cells simultaneously, the bit line become the average of the voltages that is stored in the activated cells. For reference subarray, it's VDD and VDD over 2, which is 3 VDD over 4. For the compute subarray, it's average of X and Y. So let's go one by one for the truth table. So assume for the first one, X and Y is 0, both 0. What that means is that compute subarray's bit line becomes ground, the average of 0, 0, and the reference subarray is 3 VDD over 4, and sense amplifier will compare these voltages, and since 3 VDD over 4 is higher than 0, the compute subarray cells will have 0, reference subarray cell will have 1. And for the 0, X is 0 and Y is 1, now compute subarray will have VDD over 2, but still lower than 3 VDD over 4. Still, compute subarray will have 0, reference subarray cells will have 1. And for the third one, which is the same, again, VDD over 2, lower than 3 VDD over 4, we have 0 and 1 again. So for the last case, where we have both VDD in X and Y, now the compute subarray bit line has higher voltage than reference subarray bit line. As a result of that, compute subarray cells will have 1, while the reference subarray cells will have 0. As you can see here, now compute subarray actually stores the end operation of X and Y, while reference subarray will store NAND operation of X and Y. You can imagine by manipulating this reference voltage, we can realize OR and NOR operation as well, and we can generalize it to up to N row activation. And there are more details and more hypotheses in the paper. Do we have any questions about this one? No? Yeah.
So you had
like about a 94% success rate on commercial output.
Yes.
If I understood.
Yes.
Was this an experiment to get the number, or do you also have something for the 6% where it fails, how to handle the?
It's just like demonstrating of the reliability, but it's a good question where the 6% is coming from, actually. And the characterization is the same. We sweep row addresses, timings, and the key takeaways are off-the-shelf DRAM chips can perform up to 16 input AND, OR, and NOR operations, and they can do it with very high reliability, and data pattern slightly affects the reliability of these operations. And for the first result, in the x-axis, we have number of input operands. On the y-axis, we have the success rate. And the operations are shown in different colors. And as we can see over there, off-the-shelf DRAM chips can perform up to 16 input AND, OR, and NOR operations, and they can perform it with very high success rate when it's used in 16 input. And let's see the impact of data pattern here. This is for the NOR operation, and the purple one is all ones and all zeros when the row is all one or all zero. The row is randomly initialized fully to see like how the bit line to bit line affects each other. And we see that there's at most a 2% of variation in average success rate across all number of input operands, and this trend is consistent across all tested operations. And we conclude that data pattern slightly affects the reliability of AND, OR, and NOR operations. There are a lot more things in the paper, detailed hypothesis and key ideas to perform these operations, and how the reliability of bitwise operations are affected by the location of the activated rows, how far the distance between the sense amplifier and the activated rows, the temperature, DRAM speed rate, chip density, and die revision. And we also discussed the limitations that we face while we test off-the-shelf DRAM chips. And the paper is available on arXiv. It's also open source, but I forgot to include the GitHub link. You can write the test and try to check your whether your DRAM chip is capable of computing. Let me conclude. We show that off-the-shelf DRAM chips can perform functionally complete Boolean operations, up to 16 input AND, OR, and NOR operations. And we characterize the reliability using more than 250 DDR4 chips. And we observe that they can achieve high success rates. And the operational parameters only slightly affected the reliability of these operations. And we believe that these empirical results demonstrate the potential of using DRAM as a computation substrate. So this was this paper. And for this paper, I'll just skim through it very quickly. Do we have any questions for the previous one? Yes? Yeah.
Doesn't it effectively reduces the number of subarrays to half, because we are using half of the subarrays as a negation or the positive and something.
So you're asking that now we are using two neighboring subarrays. We need two subarrays at a time. Instead of for other ones, you can, for example, parallelize in all subarrays. So actually, for real DRAM chips, we cannot do that. Since I showed you, remember that in the open bitline architecture, so two neighboring subarrays are actually connected to each other. So if you activate one subarray, you cannot use the middle one, because the data over there will be corrupted. So remember, so if we have one over there in the bit line, we will have the 0 in the other one. So you will need some isolation transistors and everything such that. So I think if you're going to implement like such isolation transistors, it could be implemented here as well. So basically, I believe because of the open bitline architecture we have, we cannot exactly using the two neighboring subarrays, even if we are not using this functionally complete operations.
Yeah. In the 6% that failed, or about 6%, how many of the bits are incorrect? Is it like 1 or 2 bits are incorrect, or is it almost your whole output is wrong?
It really changes. It depends on because so the issue is that there's a process variation. It can go up to like 30, 40%, even maybe. So we did in the next work, we did some SPICE simulations, how process variation affects such operations. So it really increases a lot. So if you have no process variation, the success rate is really good. and assuming your sense amplifier is strong enough. But if there's a process variation over there, it changes really. Like it also depends on the minimal changes even in temperature, maybe voltage fluctuations. So using real DRAM chips, it's very hard to assess what is the real problem over there. But yeah, it's good question. Some of the cells, for example, they fail all the time. Some of them are like, you can find some cells, they're 100% have the success rate of 100%. Yeah. Yes.
Was there any study or any thought on doing something that will compromise some energy, for example, overvoltage? So increasing the voltage beyond the standard to reduce the faults.
As far as I know, there's no work yet about.
When you increase the voltage,
so that could fix some of the things. Actually, we're discussing here that so we're bounded by the FPGA right now, right? Like, and it has the fixed rate of 1.5 nanoseconds. So you cannot test with, for example, we violate the timings with the interval of 1.5 nanoseconds. I cannot violate with 2. So it actually introduced some asymmetry in real DRAM. For example, the first row is activated before the other ones. So maybe increasing that voltage would help for those kind of things. I agree. And whether if like maybe more flexible or more faster clock rate would also help. But yeah, as far as I know, there is no such work yet. Yeah, great question. Any more questions? Let me skim through this one. This is published last year, DSN 2024. I think we know the motivation now, and we know the goal. We would like to understand the capability still. And for this one, we test the 120 DDR4 chips from 2 major manufacturers, and we see that we can not just perform majority of 3, we can perform majority of 5, 7, and 9 operation, and we can copy 1 row to 31 other different rows at once. And another, I think, important contribution is that, so we activate 32 rows, right? So, for example, what if I replicate the inputs of majority of 3? What if I have 10 of A, 10 B, 10 C? And how perform majority of 3 so that I improve, like I increase the voltage deviation in the bit line. So we see that it actually helps a lot. Compare the majority 3 with 3 rows or 4 rows. We increase more than 30% high, like 30% more success rate with 32 row activation. So, and this because of the, actually, we hypothesize that this is because of the process variation. So for example, if you have those 3 cells, if you have very strong cell that has more, like a lot more, let's say, capacity than others, it can dominate the charge sharing. But however, assume that you have 32 of those cells and you replicate the input. So the effect of that, let's say, strong cell will be reduced due to that. And we also test the voltage. We test undervolting, actually, for here, and see that it can affect the robustness of such operation by up to 12%. And so this is also open source and fully artifact evaluated.
The results move to the RAM.
Okay. So I already explained those things, I think. And for the multi-row copy, the key idea was RowClone. What you do is it's a consecutive activation. You activate source first and then destination, which will copy source to destination. For here, what we do is pretty straightforward. We activate source, and then we activate multiple destinations at once, and we copy the source to multiple destinations. And we see that the robustness of such operation is almost 100, but unfortunately not 100. And we conclude that off-the-shelf DRAM chips have a very, let's say, high success rate when performing a multi-row copy operation. And it's, again, available on archive, and it's open sourced and in the GitHub. And that was this paper, a very quick one. So this is the last one. Hammer, experimental analysis of read disturbance effect of processing using DRAM and real DRAM chips. I'll present this in 3 days, Tuesday, in session 5A. I guess it should be around 9 a.m. So the executive summary is, again, motivation is processing using memory is great. And prior papers show that it can perform many processing using DRAM operations, but there's an issue here. Modern DRAM is subject to read disturbance. We have row hammer. Even repeatedly activating even a single row at a time induces bit flips in unaccessed rows. So the problem is no prior study this read disturbance effect of multiple row activation, activating multiple rows simultaneously or consecutively. So our goal is to understand and analyze the read disturbance effect of multiple row activation. To this end, we test 316 DDR4 chips from 4 major manufacturers. And we observe that hammer, which we call the read disturbance effect of multiple row activation, significantly exacerbates read disturbance, causing up to more than 150x reduction in minimum hammer count induced first bit flip, which is called HC first. And the second, we observe that existing in DRAM row hammer mitigations is not effective, and hammer actually induces 11,000x more bit flips than row hammer. And we try to adapt the latest solution, industry's latest solution to row hammer, which is per row activation counting. And we observe that even adapted solution incurs an average system performance overhead of almost 50%. So for the sake of time, I'm going to skip the background. We know data movement is a real problem, and this is DRAM. And we know these operations. So we know processing using DRAM and multiple row activation is a key to realize many pod operations. One important thing maybe here is that in this paper, we try to categorize multiple row activation. We see that we have row clone, which you consecutively activate. We have like majority tree, this AND NAND operation, which you simultaneously activate. We call consecutive multiple row activation COMRA and simultaneous multiple row activation SIMRA. The consecutive multiple row activation actually, what we does is for the real DRAM chip is that we violate precharged activation timing so that we activate source and we don't trigger this hierarchical row decoder circuitry. We give enough time to deassert the intermediate signals so that we just open the destination rows only. So you just copy one row to any other row. So for the simultaneous multiple row activation, we already see that we activate once we violate this timing greatly, we activate many more rows. And one example could be majority of 3 operations where we activate 3 rows at the same time, which will perturb the bit line simultaneously. As a result of this, sense amplifier will sample the output of a majority. For this one, A, B, and B, the result is B. And the read disturbance in DRAM is a real problem, but unfortunately, even activating a single DRAM row disturbs the data integrity of other unaccessed rows. One prominent example is row hammer. When we repeatedly open and close one row, could cause bit flips in the other unaccessed rows. Here we call victim rows as the rows that experience bit flips, aggressor row as the row that we hammer. We open and close repeatedly. And because of row hammer, repeatedly opening and closing a DRAM row many times causes row hammer bit flips in adjacent rows. And that brings us to our goal and the problem. So the problem is no prior work investigates the read disturbance effect of multiple row activation, and our goal is to understand how multiple row activation will affect the read disturbance vulnerability. So we have the same testing infrastructure, DRAM Bender, and we test now 4 major manufacturers and 316 DDR4 chips. And again, we cover many derivations and chip densities here. And let's see the effect of a read disturbance effect of consecutive multiple row activation. So to hammer with COMRA, what we do is that, so for double-sided, where we sandwich a victim row with 2 aggressors, we copy from source to destination to sandwich a row, basically, here. And for the single-sided, which we have 1 aggressor and we repeatedly activate that to cause bit flips in the other victim rows, we copy 1 row to very far away another destination row so that we still have the single-sided effect, not sandwiching a row. And we again sweep a lot of parameters, row addresses, timing parameters, data pattern, and temperature. And to assess the read disturbance vulnerability, we use a widely adapted metric called HC first, which is the minimum hammer count required in this first bit flip. So lower the HC first, the worse the read disturbance is. And for that one hammer means one common operation: activate source, precharge, and activate destination. And then once we have enough hammer count, we record the bit flips in the victim. So for the first result, where we compare double-sided camera with row hammer, and the x-axis you have the manufacturers, and the y-axis you have the lowest HC first observed for manufacturer. So, and each color will represent a different operation. So here we observe that there's 14x reduction in lowest HC first when we hammer with camera compared to double-sided row hammer. And this effect is consistent across all tested for manufacturers. And now let's see how this affects each victim row. This was the lowest HC first, right? So in the x-axis, we have the test victim row percentile. And the y-axis, we have the HC first change compared to double-sided row hammer. So, and each line will represent a different manufacturer. So for example, from P1 to P100, it represents 99% of tested victim rows. And 50 to 100 represents the 50% tested victim rows. And this 50% reduction means that, for example, you observe a bit flip with 100 hammer count for row hammer, and you observe a bit flip with camera with just 50 hammer count. And we observe that more than 99% of tested victim rows experience lower HC first. And we conclude that camera exacerbates DRAM's vulnerability to the read disturbance for all 4 major manufacturers. And now let's look at the simultaneous multiple row activation. So we did exactly the same thing. We carefully sweep all the parameters that we can test. And now let's see again lowest HC first changes. So in the x-axis, you have the simultaneously activated rows from 1 to 16. One means row hammer, and the other means simultaneous multiple row activation. And as you can see here, it reduces 159x from 4,133 to 26. And this is also consistent across all tested simultaneously activated rows. And the HC first change is too much. Like again, 99% of tested victim rows experience lower HC first, and at least 25% of tested victim rows experience more than 99% of HC first reduction. This means that while row hammer have HC first of 100, Simra will have HC first of 1. And we conclude that double-sided Simra significantly decreases HC first for a majority of rows compared to double-sided row hammer. Yes. And now let's see how we can mitigate pot hammer. So the first analysis that we did, we analyzed the effectiveness of existing in DRAM row hammer mitigation against pot hammer. So there's actually an DRAM mitigation called the TRR in DDR4. So what it does is it refreshes nearby rows upon detecting an aggressor row. So here we have memory controller and TRR equipped DRAM chip. So assume TRR detected aggressor as row 2. It will issue TRR-induced refreshes to refresh neighbor rows to prevent read disturbance bit flips. And there's a paper uncovering UTRR, which reverse engineers many DRAM modules to uncover the TRR functionality, and it's available online. So we use this one to uncover what TRR the tested module has, and we try to attack the DRAM module using this information. So for the first one, row hammer, this is without TRR, and in the x-axis you see the number of aggressors that we have, and the y-axis you see total bit flips. So as we go left, we have more aggressors and more bit flips, more than 10,000. However, with TRR can detect many row hammer attacks, and we observe that there's with TRR, we observe less than 60-bit flips at most. For camera, it's similar, very similar to RowHammer. We observe 10K, more than 10K bit flips. With TRR, it's very, again, similar to RowHammer, but it induces more bit flips than RowHammer, approximately 60 bit flips. And it induces 1.1x more bit flips than RowHammer on average. So now let's look at SIMRA. So without TRR, it induces 240,000 bit flips. With TRR, it's still effective. It induces 180,000 bit flips. So we conclude that SIMRA induces 11,000 more bit flips than RowHammer on average in the presence of TRR. We believe that this is because when you issue two activation back to back, you will internally activate, for example, 32 rows. But TRR only registers the issued command. So basically, it will just register just two activation instead of 32. And then we try to adapt the RowHammer mitigations to account for PAT-hammer. What we do is that we first reduce the RowHammer threshold 4,000 to 26. And the second approach is that we try to count each operation differently depending on their lowest HC first. For example, SIMRA has 20 HC first, RowHammer has 4,000. So each SIMRA operation will be counted as 200 RowHammer activation. So for that one, we select per row activation counter, which is PRAC. You can think of that it has accurately counts activations for each DRAM row inside DRAM. So we used Remulator 2 for cycle DRAM simulator, and we tested 60 multi-program workload mixes. And in the x-axis, you see the pod workload's period of performing operations. So from left to right, the pod intensity increases. For example, 125 means DRAM performs pod operations in every 125 nanoseconds. And the y-axis, we have the normalized weighted speed up. It normalized to no RowHammer mitigation. And this is the result. So we observed that until 2 microseconds, our adapted version actually performs well compared to the naive version. But in the end, even the adapted version on average has 50% of performance overheads, and maximum it's almost 99%. And there are a lot more in the paper: the temperature, spatial variation, timing parameters, access pattern, data pattern, aggressor row on time for both multiple row activation, and the combined effect, like what if we combine SIMRA with RowHammer? We first hammer with COMRA, and then we hammer with RowHammer. How would change the HC first? So we see that there is more than 1.6x reduction in HC first on average, and we have more details and analysis on how to mitigate it. We have a discussion and qualitative analysis on how modifying DRAM chips would help mitigating PAT-hammer, and more details on the PRAC adaptation, such as like challenges. So you activate 32 rows at once, right? So you need to account this 32 row activation somehow. And an area efficient solution of PRAC, and so on. So our paper is available on archive. I guess like it's online. It's been 4 or 5 days. So let me conclude. So we extensively studied the interaction between read disturbance effects of multiple row activation. And we characterized many DDR4 chips, and we observed that PAT-hammer significantly exacerbates the DRAM read disturbance vulnerability, and it bypasses in DRAM RowHammer mitigation and uses a lot more bit flips than RowHammer. And even though we adapt the RowHammer mitigations to account for PAT-hammer bit flips, it induces almost 50% performance overheads on average. So we hope that our findings will guide system-level and architectural solutions to enable read disturbance resilient future PAT systems. Thank you for listening. I can take questions. Yeah.
I have one.
Thanks.
Going back to my previous question, so did you
Yes.
figure out work on flat hammer because of the work on the operations, because I would still expect you will find those problems. Because this is focusing on the hammering, yeah? So was it a real problem for the other work or
no, for the other work we have a very like a solved methodology. Before doing every operation, we write to the rows that we are going to work with. So there will be no bit flips such that. So yeah, you, for example, you activate 32 of them and you get the results. So you want to test it again, you write again before testing it.
On DRAM, like did you have to slow the clock to make it reliable, or did you experience any problems with really hammering on the cells in a very quick succession?
Yeah. And for that one, to prevent that one, we, for example, for a subarray, we were initializing the whole subarray again, because our goal was just to show the proof of concept capability. But definitely, if you were doing that, probably we will observe those bit flips because of this operation.
So my question was, like, did you experience or expect operating like near full clock with that, because you're violating timings of already few gigahertz clock? So that seems pretty intensive, yeah.
I think for current DRAM, we need to violate, but it's important to remember that these are just for storing data. We're trying to understand their capability. So in the future, if you would like to have this capability, we should really change things a lot. Yeah, but great question. Any more question? Yeah.
Back when you had your graphs with the number of aggressors and HC first, why did two aggressors look like an alpha?
So over there, so TRR actually tries to has a table and try to remember which rows are activated. So we are reverse engineering that sampling mechanism, which rows are aggressors. So we are playing a trick over there. So once you have more aggressor rows, so you have less activations, right? So you cannot, for example, assume that you have 4,000 of hammer count that you want to do. With 10 aggressor rows, you will have 400 each, right? But with 2 aggressor rows, you will have 2,000 each. So it will give you more chance to induce bit flips. Even TRR cannot, let's say, understand which rows are aggressors when you have 10 aggressors. You cannot induce bit flips because the hammer count is pretty low. That's why 2-row of using 2 aggressors is very efficient. You use other rows as a dummy rows to trick TRR. Yeah, these are the aggressor rows that you need. But in the meantime, you're hammering the other rows. You can think of like, it's like a buffer overflow. You have like 8 entry over there. You use 10 aggressor rows, so it will just keep the 8 rows over there. Yeah, a great question. Any more questions? Then thanks for listening. Yeah, thanks a lot. You have a question?
I have one last question. So should we stop doing research and process using DRAM?
No, we should do more. We should do more. I think these are important, but we should keep that in mind that these are still in real DRAM chips and they're not manufactured for this purpose. So in the paper, we also discussed that we can actually design DRAM chips to have this capability and also read disturbance resilient using also row hammer mitigations and also prior works like Ambit, RowClone, such design perspectives. Yeah.
That's good, especially for who is still doing a PhD. We have a research problem. Thank you very much.
Thanks a lot.
Unfortunately, due to the time, we're not going to be able to conclude the full agenda for today, but thank you everyone for sticking around. All of the material is still online. If you want to follow by yourself, we have lectures on all of those subjects already available. You can also check on YouTube. So any other burning question exists, you can always email me, Ismail or Onur, and then we can discuss online. Thank you very much once again. I hope it was an interesting workshop for you.
Thanks a lot.
Thanks a lot.